A photo of an individual using a computer, Figure 11, when it takes many roles to build a responsive design in web applications development for multiple system applications. Credit. Modification of 190,827 FND 9-12035 by Tech, SGT, R.J. Bierman/LT, Call Wilson U.S. Air Force Public Domain. Chapter Outline. 11.1 Modern Web Applications Architectures. 11.2 Sample Responsive WAD with Bootstrap and Django. 11.3 Sample Responsive WAD with Bootstrap, React, and Node. 11.4 Sample Responsive WAD with Bootstrap, React, and Django. 11.5 Sample Native WAD with React Native and Node or Django. 11.6 Sample Ethereum Blockchain Web 2 Web 3.0 application. TechWorks is creating several web applications this year for a new product line. One application is an AI image generator website and auction house for selling images. An outside consultant has been brought in, and they have determined that a hybrid Web 2.0 architecture is best suited for this solution. However, the engineering team who will perform the work needs to gain experience with Web 3.0 technologies. Therefore, the consultant recommended that TechWorks take a popular internal desktop application for managing to-do lists and recreate it as a hybrid Web 2.0 based application so engineers can gain practical experience with various web application frameworks and technologies, with the added benefit of accessing their to-dos from anywhere. The TechWorks engineering team has decided to perform iterative releases of the to-do application, starting with responsive web apps, as they will render well on various screen sizes, from large monitors to smaller displays like phones and tablets. Next, they will employ a native web application framework to target specific devices like Android and iPhones. Lastly, they will explore building a Web 2.0 based to-do application using blockchain technology, as they believe this approach will give them the necessary skills for creating future solutions. Learning objectives. By the end of this section, you will be able to understand the use of server-side rendering and MVC patterns, relate to the technology used to create responsive Web 2.0 applications, become familiar with the technology used to create native mobile applications, understand how to create Web 3.0 applications as well as hybrid Web 2.0 applications. The World Wide Web, or the web as it is known today, started as a way to link content, primarily text and images, stored on different servers or machines. It was invented by Tim Berners-Lee in 1989 while he worked as a researcher at the European Organization for Nuclear Research, CERN, home to the European Particle Physics Laboratory. Sir Tim Berners-Lee was knighted by Queen Elizabeth II in 2004 for his pioneering work. He created the Hypertext Transfer Protocol, HTTP, that operates on top of Transmission Control Protocol Internet Protocol, TCP/IP, the principal protocols used on the Internet. Clients' web browsers transmit HTTP requests to a web server, which is a software application that runs at a Uniform Resource Locator, URL, that specifies a location on the web to access it, and responds by providing pages rendered in the Hypertext Markup Language, HTML. This simple request and response paradigm, a client-server model, was easy to implement and allowed for the rapid growth of the web. This phase of the web, which began after 1989 and ended around 2004, would become known as Web 1.0, a period where the user's interaction was limited primarily to reading and selecting web pages. A web page is a document commonly written in HTML and viewed in a browser. Figure 11. 2 shows a simple Web 1.0 architecture and common usage. An encryption layer was later added to the HTTP protocol, which resulted in creating the HTTPS protocol. This made it possible to protect the sharing of sensitive information over the web from eavesdropping attacks. While web servers only served web pages initially, a common gateway interface, CGI, was subsequently added after the initial implementation of web servers to make it possible to link to applications via URLs on the web. Web 1.0 architecture and usage model, user interaction, Internet browser, Internet web server static pages, HTML 1.4, CSS 1.2, JS or scripts CGI, Figure 11. 2. This architecture outlines a user's interaction with a Web 1.0 website. Attribution, copyright Rice University, OpenStax, under CC by 4.0 license. As the web evolved from this basic architecture, the need for more dynamic and interactive experiences became apparent. Users were no longer content with simply viewing static pages. They wanted to contribute content and engage with other users. Also called online publishing, web publishing publishes content on the web while applying traditional publishing models. It was akin to digitizing an encyclopedia images and text and putting it online with hyperlinks. Today, simple websites with limited functionality, such as early blogs or static sites, still follow this model. A more interactive model that could scale to meet user demand was needed to support users' desire to provide content and interact with other users. A design pattern is a reusable solution to a common software design problem. Figure 11.3 illustrates the Model View Controller (MVC) design pattern that was employed to separate a traditional web application's data model, presentation, and business logic layers into its components. Web 2.0 Model View Controller pattern. User interacts with view. View is updated in scene. View alerts controller. Controller updates data in model. Model sends response back to view. Figure 11.3 This figure shows a user's interaction with the Model View Controller pattern. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. The original implementation of the MVC pattern on the web was such that the view would send requests to the controller, and the controller obtained data from the model and rendered it within HTML pages that were passed to browsers for presentation purposes. AJAX technology was later introduced to enable a more complete implementation of MVC on the web that allowed asynchronous updates to page components and did not require refreshing pages in the browser to fetch data. Following Moore's law, which states that the number of transistors on an integrated circuit doubles roughly every 2 years, the processing power of smaller devices like laptops, tablets, and mobile phones became the preferred way users interacted on the web. As internet data transfer speeds and bandwidth increased through better hardware, fiber optic cables, and mobile wireless technology, the rendering of web applications, interactive interfaces moved from the server side to the client side. This led to being able to run native applications, apps, on mobile wireless phones that could take advantage of specific device rendering features. In a paradigm shift that was opposite to web apps, the data model moved off the phone and onto remote servers. These solutions led to a richer user experience known as Web 2.0, which is a phase of the web focused on social interactions. This phase started in 2004, and social media websites using Web 2.0, such as Facebook, now Meta, and Twitter, now X, are well-known examples of this web phase of social interactivity. The next phase of the web, Web 3.0, which is a phase of the web where user activities may focus on decentralized access to solutions and data, is seeing a shift from the more traditional client-server model to a peer-to-peer networking model. A peer-to-peer P2P network is one in which devices connect and can share data and processing without needing a centralized server. Peers in this scheme can perform the role of a traditional client, server, or both. This shift fosters a trusted, decentralized, and open web, where large companies do not own the data, but rather where data is collectively owned by users. The use of other technologies like generative artificial intelligence, GenAI, which is powered by machine learning, aims to improve information access by mediating end-user searches to generate corresponding meaningful information out of the content available on the web. While the benefits of artificial intelligence and machine learning are vast, enabling enhanced data processing and decision-making, it is equally important to consider the risks. These technologies can pose ethical concerns, such as data privacy issues, biased algorithms, and the potential for misuse, thus highlighting the importance of responsible development and implementation. In particular, while GenAI technology is appealing and can be successful in some cases, GenAI is also known to hallucinate and generate unpredictable and often inaccurate responses to web searches. The exemplar apps of the Web 3.0 and later phases are still to be determined. Still, if the previous phases of the web are any indication, it will fundamentally change how we operate in an ever-evolving technological world. Throughout this section, we will discover how the application architectures found in Web 2.0 apps, native mobile apps, and Web 3.0 apps are designed. Global issues in technology. Importance of internationalization and localization in frameworks. Web applications are used worldwide, and specific internationalization and localization requirements must be observed to facilitate the creation of web applications that people all over the world can use. This can be challenging. To meet internationalization and localization prerequisites, services and products must be flexible to compete in international markets. This includes having the malleability to adapt to the cultural needs of target markets around the world. In global markets, language barriers are just one internationalization and localization issue that must be considered for web applications. 1. Server-side rendering and MVC patterns. The web transitioned from its 1.0 phase, where the primary usage was viewing content composed of text and images, to its 2.0 phase of user interaction. As it evolved, three technologies dominated the web's programming landscape, commonly referred to as the trifecta: hypertext markup language, HTML, a standard markup language used to describe the structure and content of web pages; cascading style sheets, CSS, a standard style sheet language used to alter the presentation style of the content found in HTML or other markup languages; JavaScript, JS, a scripting language that adds interactivity to web content and server-side functionality. Various other scripting languages and competing approaches were used prior to the adoption of JavaScript. The adoption of HTML was already a given on the web, and with the introduction of CSS in 1996, a stronger push for separating content and style was introduced so that the styling of content could be specified solely as part of style sheets rather than HTML tags. Web pages at this time mostly consisted of static content, which would be generated and delivered on the web server. Essentially, the user would select an action in their browser that sent an HTTP request to the server, such as the following. When clicking a hyperlink on a web page, the browser would send an HTTP GET request to the web server. This request asked for a specific resource, such as a web page or an image, and the server would respond by sending the requested data back to the browser. When filling out a form on a web page and clicking the Submit button, the browser would send an HTTP POST request to the server. This request included the data that was entered, like a username and password, and the server processed it and responded accordingly. Essentially, the web server performed all the HTML content rendering on the server side, and the client web browser would present what it received. The browser in this model acts as a thin client, as it has minimal functionality. Figure 11.4 illustrates the components of a traditional Web 2.0 architecture using Java-based technologies. Notice the shift in user interaction with the website compared with a Web 1.0 website. Also note that users are able to interact with applications via an application server that can retrieve data from a database or file system. This enables support for managing web sessions that allow navigation across multiple pages. Web 2.0 traditional architecture and usage model, user interaction, Internet browser, Internet web server dynamic pages, HTML4, CSS2, JS or JSP, ASP. Net application server, JavaBeans, Ado, Net, data store, SQL DBs, file systems. Figure 11. For this illustrates a user's interaction with a traditional Web 2.0 architecture. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Many of the original web applications were stateless, meaning that prior requests had no bearing on future requests. For example, it was not possible to create a shopping cart as part of a web session that would keep track of the session and what was purchased on a site and maintain the state, i.e., content in this case of the cart. In contrast, a stateful application is software that maintains the state of an application over time, while in the case of a stateless application, state is not maintained by the system and previous actions do not impact future ones. Stateless applications are simpler and easier to implement and maintain, but offer limited functionality. As previously mentioned, Web 2.0 was partly driven by user demand for more interactive functionality. Interactivity requires maintaining some state, e.g., the web session and the content of the cart as per the previous example, thereby increasing the system's complexity. This increased the demands on the web server for almost all the processing needed to generate and present the website content. Increased functionality led to more complex systems and a clear separation of responsibility between the website's rendition, business logic, i.e., the logic implemented as part of the web application, and persistence layers were needed to improve the quality and performance of the website while leveraging engineering expertise in given domains. As you learned in Chapter 10 Enterprise and Solution Architectures Management, the Model View Controller pattern is tailored to address this separation of responsibility. In the MVC pattern, the model is the persistence layer responsible for data storage and retrieval. It has a well-defined API that the controller uses. The view is the presentation layer that handles the user interface. Finally, the controller acts as the business logic layer that performs processing and enforces rules to generate applicable content within a given application domain and separates the user interface from the data. It also has a well-defined API that the view understands. The best practice design concept used to create software systems in a way that ensures weak associations with other components is called loose coupling. This concept allows for separation of concerns between components, which leads to maintaining high cohesion within websites' functionalities. MVC components are loosely coupled in that the various components can interact with one another to access the specific functionalities provided by each component. High cohesion ensures that everything that is needed to provide a specific functionality is included in one of the components. For example, on a banking website, functionality for deposits and withdrawals may be collocated on the server within the same component to ensure high cohesion. However, features for applying for a loan may be located within another component. Three popular server-side web application frameworks that implemented the MVC pattern were Apache Struts, ASP, Net, and Ruby on Rails. Concepts in practice. APIs play a large role in web services. Understanding APIs and their protocols helps determine which platform is being accessed and at what level. APIs allow access to any software with a specific purpose or functionality. APIs can be used as contracts between multiple applications. How do APIs work? The API architecture is usually explained in terms of client and server. The application sending the request is called the client, and the application sending the response is called the server. For example, in the case of an API for a weather service, the weather service database is maintained on the server side, and the mobile app is running on a client mobile device. The server side performs the majority of the functionality. It uses a combination of templated HTML, controller and application server technologies, e.g. ASP, Net, Chash, and SQL. JavaScript is sent to the browser using jQuery for cross-browser support, or it may use asynchronous JavaScript and XML to communicate with the web server without refreshing the page. Asynchronous JavaScript and XML, AJAX, exchanges small amounts of data between a client and server. The engineering team using such a web platform must understand and enforce the separation of responsibilities between the MVC components to ensure future modifications, especially significant changes, can be made without rearchitecting the system. Because the engineering team needs to know different programming languages for different layers, there may be some internal resistance to this, and it may be tempting to go around a layer to make a quick fix. Essentially, making sure that the architecture of the web platform is understood and used properly. Architectural adherence is predicated on the expertise of the engineering team members and more on the nature of the tools used. Responsive Web 2.0 applications. By the mid-2000s, JavaScript became popular for client-side browser functionality. AJAX and jQuery technologies allowed developers to create single-page applications, SPA. For the end user, SPAs offered functionality like a traditional desktop application and drastically improved user experience by reducing latency. No longer were expensive web server requests needed that resulted in full page refreshes in the browser. Instead, small data transmissions could be sent and received between the browser and server through AJAX. Figure 11.5 compares the life cycle of SPAs to a traditional Web 2.0 application. Web 2.0 traditional life cycle. Client to server, first HTTP GET, server to client rendered web page, client to server HTTP gets posts, server to client rendered web page. SPA lifecycle, client to server, first HTTP GET, server to client rendered web page, client to server AJAX, server to client JSON XML. Figure 11.5. This is a comparison of the life cycles between traditional Web 2.0 applications and SPAs. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Link to learning. The World Wide Web Consortium, W3C, develops standards and guidelines for the web. You can discover more about them and examine some of their current draft standards. jQuery, an open-source JavaScript library, ensured that web developers could write JavaScript for a generic browser document object model, DOM, that would run regardless of the user's browser. The DOM is a programming interface provided by browsers. It allows scripts, written in JavaScript for example, to interact with the structure of a web page. When a web page is loaded into the browser, the browser creates a DOM of the page. The DOM structure is a hierarchical tree-like structure that organizes the elements of the page as objects. The model used by the DOM enables dynamic access and facilitates the manipulation of content, structure, and style of web pages. Figure 11.6 illustrates a typical SPA architecture where a single web page is delivered to the browser. Note that in this model, the user's interaction with the site has increased in the amount of content generated by the user. Web 2. SPA architecture and usage model, user interaction. Internet browser HTML5, CSS3, JavaScript. Internet web server single page, application server JavaBeans Ado, net, API gateway multiples API data store, figure 11.6. This illustrates a user's interaction with a single page application, SPA. Attribution, copyright Rice University, OpenStax under CC by 4.0 license. The more sophisticated SPAs required large amounts of JavaScript on the client side. Many end users had underpowered machines or out-of-date web browsers, and the SPAs performed poorly. In the early 2010s, web application frameworks were introduced to create complex, client-side web applications that performed well, gave a native desktop application-like experience, and were easier for developers to create. These applications followed a model view model, MVVM, pattern. Figure 11.7 illustrates the relationship between the view model, and model components. Web 2.0 model view model pattern. View to view model data binding, view model to view model data change events, model to view model read, view model to model add modify delete change events. Figure 11.7 various data binding, events, and actions occur between the components of the model view model pattern. Attribution, copyright Rice University, OpenStax under CC by 4.0 license. This pattern is like the MVC pattern we've previously explored. However, several key differences exist. The following are some of the similarities and differences. The view is responsible for the presentation and only interacts with the view model. This is similar in responsibility to the view role and interaction with the controller in the MVC pattern. The view here binds to functions and properties in the view model and receives notifications on operations and changes to the data. It doesn't interact directly with the model. The model is similar to the model in the MVC pattern and is responsible for data retrieval and storage. It doesn't know anything about the view model. The view model is similar to the controller in that it decouples the relationship between the view and model and handles data manipulation. The view model responds to notifications from the model and will send events to the view if needed. Because the view binds to the view model doesn't know anything about the view. The view model can work with a local model in the browser, a remote model, or both. Unlike the previous MVC pattern regarding server-side rendering, the MVVM pattern is run entirely in the client. A representational state transfer, REST, API decouples the client-side model and view model components from the server-side business logic and persistent store. REST-based ACA-RES TFL APIs follow the architecture style designed for the web. These APIs use the JavaScript object notation, JSON, file format that represents data as text-based attribute value information. Figure 11.8 illustrates the MVVM pattern as it applies to SPA. Web 2, SPA architecture and model view model pattern, user, internet, browser, view model. Internet web server, API gateway, model S, API data store. Figure 11.8 this illustrates the model view model pattern as applied to the SPA architecture. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. As you can see from the diagram, this model is more complex than the simpler MVC pattern. The quality of the APIs partly determines the effectiveness of this pattern. REST-based APIs benefit from being discoverable, i.e., all API URIs can be found from the root API node and should be versioned, i.e., to keep track of changes to interfaces for compatibility purposes so that upgrades don't break API users. Without API versioning, coupling between client and server increases due to semantic and syntactic coupling, and upgrades become costly. Similar to a URL, a Uniform Resource Identifier, URI, is a string of characters that identifies a resource on the web. Regardless of these flaws, early browser-based frameworks proved the value of creating rich client-side apps. Web standards evolved, and newer frameworks emerged that adhered to the newer standards and solved many of the problems of their predecessors. Popular SPA frameworks include Angular, Ember, JS, React, and Vue.js. These are often used in conjunction with server-side tools, creating a full stack of technologies for developing the solution. A popular server-side technology in this stack is Node, a runtime environment for executing JavaScript code. Approaches to minimizing the data transferred between the APIs and the client to reduce network traffic or simplifying access to the data resulted in two primary approaches. One was flattening the data model. Instead of returning data in a nested format, such as from a relational database, the returned data would be flattened to a series of key-value pairs, each resulting in a unique return value. If the specific request could be made, the flattened data would be preferred to navigating the nested data to improve performance. However, creating APIs to fit specific requests could be challenging. Another solution was using GraphQL, an open-source query and manipulation language. With GraphQL, callers of its API could craft specific requests to return only the needed data, which made access to many services, such as the ones provided by microservices architectures, more scalable. Then gets through framework selection. Given that many web and native application frameworks are available today, is there a process that facilitates the selection of these frameworks? Native mobile applications. Native mobile applications are designed to run on specific mobile operating systems, i.e., Android, iOS. Android and iOS operating systems dominate the mobile device market. In 2023, Android had approximately 70% of the worldwide market share, with iOS at around 29%. Samsung, KaiOS, Windows, Linux, and others make up the remaining 1% of the market. However, in the United States in 2023, iOS was the predominant OS with roughly 61% of the market, and Android at 38%. Here we'll look at the specifics of native mobile app development by focusing on Android and iOS. 3. Native application development for Android. Native application development takes advantage of the specific features available on mobile devices. The creators of the Android operating system, OS, originally designed it as an OS for digital cameras. However, they soon pivoted and changed it to be an OS for smartphones. Today, the Android OS runs on most mobile devices worldwide. It can be found on the Google Pixel, Samsung, OnePlus, and other phones. Developers for Android mobile apps have a rich ecosystem composed of development tools, programming languages, training, and services. The primary developmental tools are Android Studio is the official IDE for Android development, built off JetBrains' IntelliJ IDEA software. Jetpack Compose is a toolkit for building native user interfaces, UI. Firebase is an app development platform and a collection of services for authenticating users, integrating ads, running A/B tests, and more. Firebase includes an A/B testing tool that helps test changes to web apps to see how changes impact key metrics such as revenue and customer retention. Developers will likely write software in Java, Kotlin, or C++. Java was historically the primary language for Android development. It runs on the Java Virtual Machine, JVM, which allows for creating platform-independent software. Kotlin is the preferred Android development language. It runs on the JVM, but also runs on the Android Native Development Kit, NDK, which is used for performance-critical parts of applications. The NDK performs better than the JVM, and it provides direct access to physical device components, e.g., sensors and touchscreen. C and C++ code can also run on the NDK. Applications developed for Android are distributed through app stores. Google Play is the principal app store, but others include Amazon App Store, HUAWEI App Gallery, and Samsung Galaxy Store. Link to learning. To explore Android app development further, Google offers free training. You can get started by creating your first Hello World Android program. Native application development for iOS. Apple's iPhone was released in 2007 and quickly dominated the mobile phone market in the United States due to its simple, intuitive touchscreen interface based on the success of its music player. The iPod contributed to its popularity. The iOS operating system runs Apple's device ecosystem, which includes iPhones, Apple TVs, Apple Watches, and more. Xcode is the primary IDE used for all Apple device development. Developers will code in Objective-C or Swift. Objective-C was the primary development language for iOS. However, it was challenging to learn. In 2014, Apple released the Swift programming language specifically designed for iOS development. It offers high-order language features, making it easier to develop software and built-in memory management, which makes less prone to crash. Industry Spotlight. Framework selection based on industry. Native application frameworks are important in every industry today. For example, mobile health applications have become quite popular. Smartwatches can collect health-related data using various sensors, and mobile health applications can leverage that data to provide useful reports to users as they exercise. Using a native application framework provides quicker load times, smooth animations and transitions, optimal security, and a seamless user experience to make it easier to immediately track and access healthcare data. Drawbacks to using native application framework include a longer development process, increased cost, complex maintenance and updates, platform dependency, regulatory and compliance issues, and end-user barriers. The benefits and drawbacks between native, web, and hybrid mobile application development. Native applications have the benefits of accessing device-specific hardware and sensors, e.g., camera, accelerometer, data, e.g., location contacts, and are optimized for performance. However, they have the drawbacks of being device-dependent and available primarily through proprietary app stores, Google Play for Android and Apple's App Store for iOS. Developers need to learn different languages and libraries for the devices. However, cross-platform development is possible with frameworks, e.g., Flutter, Kotlin Multi-Platform Mobile, allowing developers to code in a single language and run solutions on both platforms. Web apps can also run in a browser on mobile devices. They have the distinct advantage of responsiveness and can run on various screen sizes, thus allowing for a single codebase that can increase productivity and reduce cost. Disadvantages to web apps on mobile devices are limited access to hardware and software features, lower performance than native apps, and web apps may perform differently depending on the mobile browser. Traditionally, web apps didn't look like native apps. In 2017, Google introduced progressive web apps for Android, allowing web apps to look and feel similar to native apps. Finally, hybrid apps are web apps wrapped inside a native device framework, e.g., Apache Cordova. These apps have the advantages of using traditional web application development while accessing and utilizing device functions and running on multiple mobile platforms. The drawbacks are reduced speed and potential security vulnerabilities found in the framework. Concepts in practice. Software patterns and frameworks. As discussed in Chapter 9, Software Engineering, and Chapter 10, Enterprise and Solution Architectures Management, architectural styles, architectural patterns, and design patterns are typically used to enforce the quality attributes of software solutions. To facilitate the creation and maintenance of web applications and scalable transactional websites, web application frameworks and native application frameworks that leverage applicable patterns, such as MVC, were created and improved over the past couple of decades. Web frameworks are used within web application frameworks to facilitate the use of HTML5, CSS3, and JavaScript, and to publish responsive web pages that can be rendered by modern browsers on all modern target devices. Web application frameworks help process UI-driven requests that result in publishing or updating web pages. Native application frameworks take advantage of capabilities available on specific target devices, such as iPhones and Android phones. Organizations in many industries rely on web applications and related frameworks to conduct business daily. Web 3.0 applications. Web 3.0 is the next phase of the web. It is still being realized, and similar to Web 1.0 and 2.0, it can only be fully understood in hindsight. The technology and uses of the web overlap between the phases, with newer phases becoming preferred over their predecessor phases. If Web 1.0 was the read-only web, and Web 2.0 was the participation, write, web, then Web 3.0 may be the read, write, and execute web. Tim Berners-Lee had referred to Web 3 as the semantic web, a system of autonomous agents, which are software programs that respond to events. That model has shifted over the years, while AI and other technologies such as AR/VR will likely form a part of Web 3.0 or WebX0. The principles that govern the next phase are expected to be around a web that is decentralized, permissionless, and trusted. Web 3.0 sees a shift from the more traditional client-server model to a peer-to-peer networking model. A peer-to-peer network is one in which devices connect and can share data and processing without needing a centralized server. Peers in this scheme can perform the role of a traditional client, server, or both. This shift will foster a trusted, decentralized, and open web, where large companies don't own the data, but everyone collectively owns it. Technologies such as a smart contract allow a trusted model that is needed in a decentralized system. Artificial intelligence and machine learning will improve information access through understanding the meaning of content available on the web. The exemplar apps of the Web 3.0 phase will be defined in the future. Still, if the previous phases of the web are any indication, it will fundamentally change how we operate in an ever-evolving technological world. Finally, Web 3.0 apps will run on a web that supports Web 1.0 and 2.0 apps, with the likely result being hybrid architectures that are partially Web 2.0 and 3, Web 3.0 application architectures. Web 3.0 apps are architected without a centralized server, so they are considered to be decentralized apps, DApps, which are applications that execute smart contracts and run over distributed ledger technology, DLT. Smart contracts are programs that can be executed on a distributed ledger. Distributed ledgers use independent network nodes to record, share, and synchronize transactions in their respective electronic ledgers instead of keeping them in a centralized server. The code is visible to all parties, and trust is put into the code instead of a centralized third party. Distributed ledgers chronicle transactions between accounts that are recorded in multiple places. Blockchain is a type of DLT. Let's compare a traditional Web 2.0 application with a 3.0 DApp. In Web 2.0, if you created a website for users to post pictures and make comments on them, you would need functionality for authenticating users, authorizing their actions, generating a UI for adding images, browsing images, and posting comments. To do this, you would need a front-end web server and back-end processing for business logic and data storage. These servers would run in a company's data center or on a cloud provider. The company would own all the code and data, including metadata about how you interact with the website, e.g., what you commented on, how long you looked at a pictures. As a reminder, Figure 11.4 illustrates a traditional Web 2.0 architecture. Note, for our purposes, the SPA architecture could also be used here. In a Web 3.0 DApp, the functionality for creating an application for posting pictures and commenting on them would remain the same. The principal differences would be where the code runs and who owns the code and data. Let's break this down into a series of steps that shift away from a centralized solution to a distributed one. To start, we can keep the web server's front end and replace the back-end code with the distributed application. The Ethereum blockchain, as an example, is a deterministic state machine that runs on a peer-to-peer network. A deterministic state machine has a model of computation that relies on a finite number of states and transitions between them to respond to inputs. It guarantees a single transition from one state to another in response to an input. Because it is based on a deterministic state machine, the Ethereum blockchain is often referred to as a world computer. Ethereum blockchain transactions are calls to methods that are implemented in smart contracts. These method calls result in change to the data, ACA, state, that is maintained by the contracts within the blockchain. The Ethereum blockchain records transactions into blocks that are added to its blockchain. Changes to the state machine itself, e.g., modify the block or transaction data structures used in the Ethereum blockchain, require consensus between the node providers that support the peer-to-peer blockchain network. Anyone in the world can read or write to the machine. A central authority does not govern it. Smart contracts form the code and are written in high-level languages like Solidity or Viper. The high-level contract code is compiled into bytecode that can be executed on the Ethereum virtual machine, EVM. Each block contains a hash pointer of the previous block, with a timestamp and the transaction data. The hash pointer includes a cryptographic hash, i.e., a fixed-size digest of the previous block that makes it possible to verify that the previous block was not changed since it was stored in the blockchain. The cryptographic part ensures that the hash value has some special properties, and in particular, that the original data cannot be derived from the hash value. Figure 11.9 replaces the traditional back-end components of a website with a blockchain. The user's interaction with the website is consistent with a traditional Web 2.0 website, as the back-end processing is hidden from the user, though it has been replaced with a blockchain node. Web 3.0 DApp architecture: web server and blockchain. User, internet browser. Internet web server, JSON-RPC, blockchain, smart contract, S, blockchain VM, block S, Figure 11.9. Here is a traditional Web 2.0 website with back-end components replaced with a DApp. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. In the figure, the web server talks to a node of the blockchain, referred to as a full node. A full node is a computer that maintains a copy of the blockchain and runs blockchain software. Operating a full node can become expensive because you need to provide the hardware and pay a fee to join the Ethereum network. Blockchain end users typically use a software wallet such as MetaMask to access nodes in the blockchain, or use a third-party wallet offered by providers like Infura, Alchemy, or QuickNode. MetaMask is a wallet technology that stores a user's private keys in their browser. Blockchain providers use the JSON-RPC specification for managing communication from clients' end users. This remote procedure call, RPC, is lightweight and transport agnostic. As previously mentioned, any client can access the blockchain via a wallet provider, which requires creating an account and obtaining a wallet ID. Once logged into their wallets, clients can perform blockchain transactions, which end up reading and/or writing to the blockchain and changing the state of smart contracts. The wallet ID is used to sign transactions so they can be traced to the client wallet. In our example, browsing photos on the Web3.0 application is a red transaction that would not require signing anything. However, adding photos and comments would. Adding data to the blockchain incurs a cost as nodes now need to store that data. The user incurs this expense. Imagine paying every time you upload a photo to your favorite social media app. Instead of storing the data on the blockchain, a cost-effective approach would be to store the data using the Interplanetary File System, IPFS, protocol. IPFS is a peer-to-peer distributed file-sharing protocol. You can go through a provider like Pinata to get a hash value for the data, i.e., a fixed-length digest of the data that cannot be used to obtain the original data. You upload to the IPFS and store that hash value in the blockchain via a smart contract interface, thereby reducing the storage cost of data within the blockchain. Figure 11.10 shows the addition of the provider between the web server and the DApp, a signer for when the user wants to write to the application. The inclusion of the IPFS for data storage. Web's 3.0 DApp architecture with provider, signer, and IPFS. User, Internet Browser Signer. Internet Web Server, JSON RPC, Provider, IPFS Swarm. Provider Blockchain Smart Contract, S, Blockchain VM Block S, Figure 11.10. This architecture has added a signer, provider, and IPFS. Attribution. Copyright Rice University, OpenStax, under CC BY 4.0 license. Up to this point, we've kept the front-end logic on a web server hosted in a centralized location. This is a good temporary approach for an organization that wants to transition a legacy solution to a DApp over time. Because IPFS will host some of the data of the DApp, let's move the front-end HTML, CSS, and JavaScript there and load it into the browser like in SPA app. Like in SPA, we want the application to run asynchronously and respond to events like changing data as they occur. Web3. JS is a JavaScript library that uses the JSON RPC to respond to events fired when smart contracts execute. Alternatively, the Graph is a solution that uses GraphQL to make it easier to query data on the blockchain. Figure 11.11 shows the updated architecture with the front end residing in IPFS and the addition of the Graph, listed as GraphQL, for improved querying of the blockchain. Web3.0 DApp architecture with IPFS and graphing. User, Internet Browser Signer. Internet IPFS Swarm Signer. JSON RPC. Provider IPFS Swarm. GraphQL Blockchain Smart Contract S. Blockchain VM Block S. Figure 11.11. The front-end web page has been moved to IPFS and graphing query capabilities have been added. Attribution. Copyright Rice University, OpenStax, under CC BY 4.0 license. This results in a Web3.0 application. However, there are problems with this architecture that we will examine next. Web3.0 application challenges. Blockchains currently have a scaling problem. The average size of a block has increased over the years, and transaction fees are associated with each transaction. A common fee is the gas price, which is the cost of validating transactions and updating ledgers. Additionally, negative performance can occur on a blockchain with large amounts of transactions. One approach to help with scaling is the use of sidechains. A sidechain is a secondary, i.e., level 2 or L2 blockchain that increases the blockchain network performance by aggregating transactions off-chain, off the mainnet/Ethereum network, and committing them to the mainnet at once. Polygon is a popular L2 scaling system for sidechaining. Other L2 scaling techniques include blockchain rollups, which are protocols designed to enable high throughput and lower costs. They address scaling by bundling transactions and reducing data sizes to increase transaction efficiency and limit storage costs. Examples of blockchain rollups include optimistic and zero-knowledge rollups. An optimistic rollup is a protocol that increases transaction output by bundling multiple transactions into batches, which are processed off-chain. In this case, transaction data is recorded on the mainnet via data compression techniques that lower cost and increase transaction speed. Optimistic rollups on Ethereum can improve scalability by a factor of 10 to 100. A zero-knowledge rollup, ZK rollup, is a protocol that bundles transactions into batches that are executed off the mainnet. For every batch, a ZK rollup operator submits a summary of required changes once the transactions in the batch have been executed. Operators have also produced validity proofs that demonstrate that the changes are accurate. These proofs are significantly smaller than transaction data, so it is quicker and cheaper to verify them. Additionally, ZK rollups are used on Ethereum to reduce transaction data size via compression techniques, which ends up reducing user fees. Figure 11.12 shows the addition of sidechains to the architecture to mitigate some of the challenges associated with Web3.0 dApps. Notice how the user's interaction with the Web3.0 app has grown from mostly reading content in a Web1.0 model to more fully participating in the content and functionality of the Web3.0 app. Web3.0 dApp architecture and usage model. User interaction, Internet Browser Signer, Internet IPFS Swarm Signer, JSON-RPC Provider IPFS Swarm, JSON-RPC GraphQL Blockchain. Sidechains Blockchain Smart Contract S, Blockchain VM Block S, Figure 11.12. The user's interaction with the full Web3.0 application is highlighted here. Attribution. Copyright Rice University, OpenStax, under CC BY 4.0 license. As you can see, the architecture has become rather complex to support dApps effectively. However, Web3.0 is still in a nascent phase, and currently there are several solutions and tools being developed to make building and deploying Web3.0 dApps even easier. Hardhat is a developer ecosystem for building and deploying smart contracts on a local network for testing. This architecture focused on blockchains and used Ethereum as the principal implementation. However, there are other DLT solutions. Hashgraph is an approach where only selected nodes store the entire blockchain, and voting mechanisms are introduced to validate if the blocks are correct. Stacks is another DLT where only the smart contracts are decentralized, and the data is controlled by its owner. Owners can share or remove it, ensuring data privacy. Technology in everyday life. Use of frameworks. Web applications are used today to power commercial websites that are accessed by people to complete online transactions to buy goods of any kind. Mobile web applications and native versions of such are also available on smartphones and watches to help do the same. How does using web and native application frameworks help people in everyday life? Provide a couple of illustrative scenarios to explain your opinion. Your scenarios should not be limited to describing how the frameworks are used, but rather describe situations where these frameworks are applied in real life. Hybrid Web 2.0.3.0 applications. Due to the qualities and limitations of Web 2.0 and 3.0 architectures, it is likely that we'll see solutions that are a combination of the two approaches and leverage their best attributes. One way to do this would be to have workflow processes that require a high rate of change implemented in a Web 2.0 architecture, while processes that would benefit from using a distributed ledger being executed in Web 3.0. For example, traditional commercial websites can keep using the Web 2.0 architecture, while payment solutions can be extended by accessing the Web 3.0 architecture to make payments using cryptocurrencies, e.g. Bitcoin. Let's consider an app for generating AI artwork. Many solutions exist today for doing this. However, we want our app to give ownership to the digital artwork a person generates. AI models are trained to recognize existing artwork, e.g., paintings available via the WikiArt.org API that may be copyrighted, so ownership is still being determined in the courts. Here, the term ownership is used to attribute AI image creation and nothing more. While AI models are very popular, some companies do not want to share data with AI model creators and prefer to have the AI models deployed in their own infrastructure to ensure full privacy. A non-fungible token, NFT, is a unique digital identifier on a blockchain that a user may want to create of their image and possibly sell, i.e., transfer ownership, on a marketplace. A common use case for this app might be, a user logs into the website and enters a prompt to generate an image. After several rounds of adjusting their prompts, they end up with an image they want. The user pays to have a non-fungible token created of the image, which is stored on a blockchain marketplace for sale. As you can imagine, running an AI image generator on a blockchain might not perform well. Likewise, creating NFTs without blockchain technologies is counterintuitive. Therefore, the architecture for this solution needs to encompass both Web 2.0 and 3.0 approaches. Figure 11. 13 shows how the APIs will do the heavy lifting of working with the AI model to generate the artwork. Once the user is satisfied, they will interact with aspects of the UI that execute smart contracts to generate and add the NFT to the blockchain. Transactions will happen on the blockchain. APIs may interact directly with the blockchain, looking for similar works. Web 2.0 and 3.0 hybrid architecture. User, browser, JSON XML, API gateway. Browser Internet Web Server, API Gateway, API S, Datastore S, API S, JSON RPC Provider Blockchain, Signer Provider Blockchain Smart Contract S, Blockchain VM Block S. Figure 11. 13. This outlines the user's interaction with a hybrid Web 2.0 3.0 application. Attribution, copyright Rice University, OpenStax under CC by 4.0 license. This model still has a centralized Web 2.0 server for artwork generation and account management. However, portions that deal with NFT ownership and selling of that ownership are managed within the Web 3.0 blockchain infrastructure. This approach serves the needs of many businesses that want to take advantage of Web 3.0 features while preserving their original Web 2.0 websites. Learning objectives. By the end of this section, you will be able to create a to-do web application with Bootstrap and Django. Create a Django project. Create and register a to-do app. Define the to-do model. Set up the Django REST APIs. Create the user interface. In this module, you will create a simple, responsive to-do application. To accomplish this, you will use Bootstrap and Django. Bootstrap is an open-source, responsive web application framework, and Django is a Python-based web application development framework. Both frameworks are highly popular due to their ease of use. Creating a to-do web application with Bootstrap and Django. The to-do web application in this subsection uses Bootstrap and Django. Bootstrap CSS templates are used for the UI features. Django serves as both the front end and back end. Django templates are part of the user interface to get and set data via HTTP requests. Incoming requests are then handled by an API built using the Django REST framework. Prerequisites. To build the to-do application, you must install Python, pip, Django, Django REST framework, Bootstrap, and jQuery. The to-do application on the following pages was developed and tested with specific software versions. To avoid errors, please ensure you install the same versions: Python v3, 9.4, pip v21, 3. 1 Django v4, 0.1 Django REST Framework v3, 13.1 Bootstrap v4, 5.0 and jQuery v3, 5.1. The steps to build the to-do application are as follows. Install and set up a local programming environment for Python 3. Download and install Python 3.9.4 Figure 11. 14 shows adding Python and its scripts subfolder to your path environment data. On Windows, the path updates might be C /users /your username /app data /local /programs /python 39 and C /users /your username /app data /local /programs /python 39 /scripts. Edit environment variable window shows adding Python and its scripts folders. Figure 11. 14. This is what appears when adding Python and its scripts folders to the environment variables path on Windows. Used with permission from Microsoft. Create a Python venv, Python mvenv py 394 venv. Activate the venv, cd py 394 venv. Windows /scripts /activate, bat. macOS source bin activate. Install in the local programming environment Django. Pip install Django == 4, 0. 1. Install in the local programming environment Django REST Framework. Pip install Django REST Framework == 3, 13.1. Figure 11. 15 shows the sequence of steps needed to install the Python environment for working with Django and the Django REST Framework. Sequence of steps needed to install the Python environment. Figure 11. 15. This screenshot displays the sequence of steps needed to install the Python environment. Used with permission from Microsoft. Creating the Django project. The first step to building a Django web application is to create a Django project, which is a high-level directory used to contain the directories and files necessary to run a Django web application. To create a Django project, run the following commands: mkdir bootstrap Django to do app, cd bootstrap Django to do app, $Django admin start project to do app. The period at the end of the last command is very important to ensure that Django-dependent files are generated in the current directory. By following these commands, the directory bootstrap Django to do app / will be created, and Django-dependent files will be generated as shown in Figure 11. 16. Directory bootstrap Django to do app includes Django-dependent files, pycache static init, pyasgi, pysettings, pyurls, pywsgi, pydb, SQLite 3 manage, Figure 11. 16. The directory bootstrap Django to do app / includes these Django-dependent files. Rendered in Django, a registered trademark of the Django Software Foundation. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Django built-in database tables are used to manage users, groups, migrations, and so forth in a web application. To generate these tables, run the migrate command, python manage, pymigrate. The final step to creating a Django project is to confirm that the setup was completed. To do this, run the runserver command shown here. Python manage, pyrunserver. To further confirm that the Django project setup was completed, launch a browser and navigate to http://localhost 8000, Figure 11. 17 shows the Django page. Django page shown once project setup is complete. The install worked successfully. Congratulations, Figure 11. 17 Once the Django project setup is successfully completed, this page should appear at http. Localhost 8000. Credit: Django is a registered trademark of the Django Software Foundation. Link to learning. Django is a free and open-source Python web framework that can make web development more efficient and less time-consuming. With an emphasis on streamlining web development and making it easier for web developers to meet deadlines, Django also requires less code, creating and registering the to-do app. Once the Django project is successfully completed and set up, the next step is to create the to-do application and register it in the Django project. To accomplish this, run the following command, python manage, pystartapp-todo. The to-do / directory will be generated under the Django project directory, bootstrap Django to-do app /. Files related to the to-do application will be generated as shown in Figure 11. 18. To-do / directory generated under the Django project directory, pycache, migrations, static init, pyadmin, pyapps, pymodels, pytests, pyurls, pyviews, Figure 11. 18. This shows the to-do / directory, which is generated under the Django project directory, bootstrap Django to-do app /. Rendered in Django, a registered trademark of the Django Software Foundation. Attribution: Copyright Rice University, OpenStax, under CC by 40 license. Next, the to-do application must be registered in the Django project as an installed app so that Django can recognize it. To do this, open the to-do app settings, pyfile, look for the installed apps variable as seen in Figure 11. 19. Add to-do to the list as shown. Because the Django REST framework will be used, also add REST framework to the list. A list of installed apps includes REST framework and to-do. Figure 11. 19. To register the to-do application in the Django project as an installed app, the list of installed apps should include REST framework and to-do. Rendered in Django, a registered trademark of the Django Software Foundation. Attribution: Copyright Rice University, OpenStax, under CC by 40 license. Define the to-do model. Once you register and install the to-do web application, you will be able to create to-do tasks, which can be assigned categories. The next step is to create the models. 2 models will be created for category and to-do list. Open the to-do /models, pyfile and add the code shown, #* coding. UTF-8*. From future, import Unicode literals. From Django, DB import models. From Django, utils import timezone. Create your models here. Class category models. Model name equals models. Char field max length equals 100. Class meta verbose name equals category. Verbose name plural equals categories. Def str self return self name. Class to-do list models. Model. Title equals models. Char field. Max length equals 250. Content equals models. Text field blank equals true. Created models. Date field default equals time zone. Now. SDRF time %Y%M%D. Due date equals models. Date field default equals time zone. Now. SDRF time %Y%M%D. Category equals models. Foreign key category default equals general on delete equals models. Do nothing. Class meta ordering equals created hash order by most recently created. Def SDR self return self. Title. The category and to-do list Python classes describe the properties for the models for category and to-do list tables, respectively. The to-do list model contains a foreign key field to the category model. Each to-do item will be associated with one category. After creating the models, a migration file needs to be generated to create the physical tables in the database. To generate the migration file, run the following command. Python manage py make migrations to do. This command will generate a migration file in to-do/migration/, which will look like the following code. Hash generated by Django 40. 1 on 2020-130-21, 14. From Django, db import migrations, models. Import Django db, models, deletion. Class migration, migrations, migration. Initial equals true. Dependencies equals. Operations equals. Migrations, create model. Name equals category. Fields, id models, big auto field. Auto created equals true. Primary key equals true. Serialize equals false. Verbose name equals ID. Name models. Char field max length equals 100. Options. Verbose name category. Verbose name plural categories. Migrations create model. Name equals to-do list. Fields. Id models. Big auto field auto created equals true. Primary key equals true. Serialize equals false. Verbose name equals ID. Title models. Char field max length equals 250. Content models. Text field blank equals true. Created models. Date field default equals 2022-01-30. Due date models. Date field default equals 2022-01-30. Category models. Foreign key default equals general on delete equals Django. db models deletion. Do nothing to equals to do. Category. Options. Ordering createds. The next step is to apply the changes in the migration file to the database, which is accomplished by running the following command. Python manage py migrate. For this application, Django uses the default SQLite3 DB SQLite3 database. Please note that Django supports other databases as well, including MySQL and PostgreSQL. To define the to-do model, you can use the default Django admin interface to perform CRUD operations on the database. To use the admin interface, open the to-do/admin. Py file and register the models as seen in the following code snippet. # coding, UTF-8 *. From future import Unicode literals. From Django contrib import admin. From import models. Register your models here. Class to-do list admin model admin list display equals title created due date. Class category admin model admin list display equals name. Admin site register models to-do list admin. Admin site register models category admin. The next step is to create a superuser account that allows access to the admin interface. To do this, run the following command and follow the prompts to enter a username, email address, and password for the superuser. Python manage py create a superuser. Once this step is complete, restart the server using the following command. Python manage py run server. After this is complete, open a browser and navigate to http://localhost 8000 admin to access the admin interface. Log in with the credentials that you set up for the superuser. When you log into the admin interface, you should see the following page from Figure 11.20. On this page, you will have the ability to create, edit, and delete categories and to-do items. The Django administration interface shows site administration tools to create, edit, and delete categories and to-do items. Figure 11.20. The admin interface is where superusers can create, edit, and delete categories and to-do items in the To-Do web application. Rendered in Django, a registered trademark of the Django Software Foundation. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Setting up the Django REST APIs. Previously, you installed the Django REST framework, which provides a toolkit to build APIs. In this section, you'll create the serializers, view functions, and routers required for the API, creating the serializers. The next step is to implement two serializers, one for the category model and one for the to-do list model. A serializer is a tool to control response outputs and convert complex data into content, such as JSON. In the to-do directory, create the file serializers. And add the code shown in the code snippet that follows. The serializer classes inherit from serializers. Model serializer because this class creates the serializer, with fields corresponding to the model fields defined earlier. Each serializer specifies the model to work with and the fields to be included in the JSON object, which are all fields. #to-do/serializers. From REST framework, import serializers. From models, import to-do list category. Class category serializer serializers. Model serializer class meta model equals category. Fields all. Class to-do serializer serializers. Model serializer class meta. Model equals to-do list. Fields all. Creating the view. After you create each serializer, the next step is to create a corresponding view function for both the category serializer and the to-do serializer. To do this, open to-do/views. And add the code shown in the code snippet that follows. The views class, which provides a default implementation of the CRUD operations, is imported from REST framework. The category view and to-do view classes provide a query set of categories and to-do items, respectively. They also specify the serializer class defined in the previous section. #*coding. UTF-8*. From future, import Unicode literals. From Django, shortcuts import render, redirect. From REST framework, import views. From serializers, import to-do serializer, category serializer. From models, import to-do list, category. Import data time. #create your views here. Class category view views. Model view set, query set equals category, objects. All. Serializer class equals category serializer. Class to-do view views. Model view set, query set equals to-do list, objects, all. Serializer class equals to-do serializer. Creating the routers. The next step is to create the routers that provide URL paths for the API. To do this, open the to-do/URLs file and add the code shown in the code snippet that follows. From Django, URLs import path include. From to-do, import views as to-do views. From REST framework, import routers. From to-do, views import. Router equals routers, default router. Router, register, are categories, category view, base name equals categories. Router, register, are todos, to-do view, base name equals to-dos. URL patterns equals, path index name equals to-do list. Path RAP/ include router. URLs. Once you complete this step, launch the Django server using the following command, python manage, run server. To access the API, launch a browser and navigate to http. 127.001.8000/API/. As shown in Figure 11. 21, you should see two API paths listed, one for categories and another for to-do items. Screenshot of API paths, one for categories and one for to-do items. Figure 11. 21. Once the URL paths for the API are created, two API paths are listed, one path for categories and the other for to-do. Rendered in Django, a registered trademark of the Django Software Foundation. Attribution, copyright Rice University, OpenStax, under CC by 40 license. To-do items are dependent on categories. To perform CRUD operations on the category table, click on the categories API path, as shown in Figure 11. 22. Screenshot of category list with API path, Figure 11. 22. The API path can be used to perform CRUD operations on the category table. Rendered in Django, a registered trademark of the Django Software Foundation. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Once you access the category list page, enter a category name in the field near the bottom of the page and click the Post button to save it. You can add additional category names. Once you save each name using the Post button, the categories will appear in JSON format, as illustrated in Figure 11.23. Screenshot of JSON format on category list. Figure 11.23. The category list is created in JSON format after saving category names. Rendered in Django, a registered trademark of the Django Software Foundation. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. To ensure that categories can be updated or deleted as needed, the primary key, which is id, must be included in the API path g/API/categories/ID/. For example, to update or delete the category with ID equals 3, the API path is /API/categories/3/, as shown in Figure 11.24. Once this category is pulled up on the category instance page, the delete button is visible at the top to delete the category. If the category needs to be updated, the PUT button visible near the bottom can be used for updates. Screenshot of category instance displaying delete and PUT buttons. Figure 11.24. The category instance page provides delete and PUT buttons, which, respectively, can be used to delete or update a category. Rendered in Django, a registered trademark of the Django Software Foundation. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Next, navigate back to the API root. Click on the To-Do's API path to see, as outlined in Figure 11.25, that a to-do item has a category field that appears as a drop-down list of categories. The CRUD operations also can be performed on the to-do list table. This will be done next through the user interface via templates. Screenshot of to-do list with drop-down category showing work and personal. Figure 11.25. After the routers are created, a to-do item has a category field that appears as a drop-down list of categories, such as work and personal. Rendered in Django, a registered trademark of the Django Software Foundation. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Creating the user interface. To use and control the to-do application, you must create a user interface, UI. This section will outline the steps to do this. Installing Bootstrap. The first step to create a UI is to install Bootstrap, which, as an open-source, responsive web application framework, can be used in web applications like Django to create UIs. To install Bootstrap in a Django application, you have several options. In this scenario, an efficient method is to download the Bootstrap CSS and JS files and add them to the static directory, as shown in Figure 11.26. To do this, first create the static directory in the Django project directory. In addition, to install jQuery, download the JS file and add it to the static directory. Finally, add a custom CSS file to include individual style in the Django web application. Screenshot of static directory with CSS and JS files listed. Figure 11.26. An efficient method to install Bootstrap in a Django application is to download the Bootstrap CSS and JS files and add them to the static directory. Rendered in Django, a registered trademark of the Django Software Foundation. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. After adding the CSS and JS files to the static directory, the next step is to open the To-Do app settings. Py file, navigate to the bottom of the file, and add the path variables shown in the following code snippet. #static files, CSS, JavaScript images, #HTTPS, docs, Django project, common 4, 0/how/to/static files /static URL equals static, project root equals os. Path, dir name os, path, obspath file, static root equals os, path, join project root, static, creating the view. The next step is to create the view. The view function is needed for template pages, which are created in the next section. The view function is also needed to interact with the database to both create and delete to-do items. To create the view, open the to-do/views. Py file and add the code shown in the following code snippet. This code takes an HTTP request object. If the request method is post, a to-do item is either created or deleted, depending on which button is clicked. Otherwise, the request method is GET and the to-do items are displayed to the user. Def index request, #index view to-dos equals to-do list. Objects, all, #query all to-dos with object manager categories equals category. Objects all, #get all categories with object manager if request. Method equals post, #check if request method is post if task add in request, post. Hash check if request is to add a to-do item title equals request. Post description hash title date equals str request. Post date hash date category equals request. Post category select hash category content equals title plus date plus category hash content to do equals to-do list. Title equals title, content equals content, due date equals date, category equals category. Objects get name equals category, to do. Save, hash save to do item return redirect, slash, hash reload page if task delete in request. Post, hash check if request is to delete a to-do checked list equals request. Post checkbox hash check to-dos to be deleted for to-do ID in checked list. To-do equals to-do list. Objects, get, ID equals int to-do ID, hash get to-do id to-do. Delete, hash delete to-do return render request, index, HTML, to-dos, categories. Creating the templates. The final step to build a Django web application is to create templates, which are HTML files that can also contain embedded Python code. Create a file called style, CSS under the /static/CSS directory and insert the code shown here into that file. The templates discussed in the following sections require this style sheet. /basic reset ***, before ***, after WebKit box sizing, border box moz box sizing, border box sizing, border box. App */HTML font size, 100%, body background, #E6F9FF, font family, Open Sans serif, super basic grid structure. Container width 600px, margin, 0 auto, background, FFFFFF, padding, 20px0, WebKit box shadow, 002px RGBA 00002. Box shadow 002px RGBA 00002, row display block padding 10px, text align center, width 100%, clear both overflow hidden, half width. 50% float left, content background FFF, logo */H1 font family, rocket sans serif color 666, text align, center, font weight 400, margin. 0 tagline margin top -10px, text align, center padding 5px 20px, font size 11px, font weight 600, text transform, uppercase color 777. Inputs *, input container height 60px, border top 1px solid E5 position relative overflow hidden, input container, last border bottom 1px solid E5 margin bottom 20px, input container half last right border left 1px solid FFF. Input type equals date, input type equals text, select height 100%, width 100%, padding 020px, position absolute top 0, vertical align, middle display, inline block, border none. Border radius none, font size 13px, color 777, margin 0, font family, Open Sans serif, font weight 600, letter spacing 0.5px, WebKit transition. Background 0, 3's transition, background 0. 3's, input type equals date, cursor pointer, input type equals date, focus, input type equals text, focus, select, focus, outline, none, background. X0 F1, WebKit input placeholder, color, light gray, font weight, normal, WebKit transition, all 0, 3's transition, all 0, 3's, moz placeholder, color, light gray, font weight, normal, transition, all 0, 3's. MS input placeholder, color, light gray, font weight, normal, transition, all 0. 3's, input moz placeholder, color, light gray, font weight, normal, transition, all 0. 3's, input focus, WebKit input placeholder, color. 95A5A6, font weight, bold, input focus, moz input placeholder, color, 95A5A6, font weight, bold, input container label padding, 5px 20px, font size. 11px, font weight, 600, text transform, uppercase, color 777, display, block, position absolute, button, font family, Open Sans serif, background transparent, border radius 2px, border none, outline none, height 50px, font size 14px, color FFF, cursor pointer, text transform, uppercase, position relative, WebKit transition, all 0, 3's transition, all 0, 3's. Padding left 30px, padding right 15px. Icon, position, absolute, top 30%, left 10px, font size 20px, taskad background 444, padding left 31px. Taskad hover background 303030, task delete background E74C3C, padding left 30px, task delete hover background C392B. Task styles task list style, none padding 020px, task item border top 1px solid E5 padding 15px0, color 777, font weight 600, font size 14px, letter spacing 05px, task list, task item, nth child even, background, FCFCFC. Task checkbox margin right, 1M, complete true text decoration, line through, color BBEB, task list, task date color 95A5A6, font size 10px, font weight, bold, text transform uppercase. Display block margin left 41px, calendar margin right 10px, font size 16px, class asterisk equals category, display, inline block font size 10px, background 444, vertical align, middle color, FFF padding 10px, width 75px, text align, center border radius 2px, float, right, font weight, normal text transform, uppercase. Margin right 20px, category background transparent, category personal background 2980b9, category work background 8e44 add, category school background F39c12, category cleaning background 16a085, category other background D35400, footer text align center, font size 11px, font weight 600, text transform, uppercase, color 777, footer a color F39c12, custom checkboxes asterisk, task checkbox, WebKit appearance, none, appearance none. WebKit transition all 0, 3s transition all 0, 3s display, inline block, cursor pointer width 19px, height 19px, vertical align middle, task checkbox, focus, outline, none, task checkbox before. Task checkbox checked before font family, font awesome, color 444, font size 20px, WebKit transition all 0, 3s transition all 0, 3s, task checkbox before content. Backslash F096, task checkbox checked before content, backslash F14A, color 16A085, custom select menu, task category, WebKit appearance, none. Appearance none, cursor pointer, padding left, 16, 5px, slash asterisk specific positioning due to difficult behavior of select element asterisk slash background, FFF, select arrow, position, absolute, z-index 10. Top 35%, right 0, margin right 20px, color 777, pointer events none, task category option, background, FFF, border none, outline, none, padding. 100px, the first template file is base HTML, which is the file that includes links to Bootstrap and jQuery. To illustrate these links, a snippet of the base HTML file is shown in the code. The Bootstrap navigation bar is implemented in this file. doctyp HTML head meta charset equals UTF-8 slash title to do app Django slash title % load static %. Bootstrap CSS link rel equals stylisheet href equals slash static slash CSS slash bootstrap. Min CSS slash link rel equals stylisheet, type equals text slash CSS, href equals HTTPS. Maxdin bootstrapdin, com font awesome 4, 70 slash CSS slash font awesome. Min CSS slash link rel equals stylisheet, type equals text slash CSS, href equals % static CSS slash style. CSS % slash jQuery script type equals text slash JavaScript, src equals % static JS slash jQuery 3. 51 min JS % slash script. Popper script type equals text slash JavaScript, src equals % static JS slash popper, min JS % slash script. Bootstrap core JavaScript script type equals text slash JavaScript, src equals % static JS slash bootstrap. Bundle min JS % slash script slash head body nav class equals navbar dark bg dark justify content between a class equals navbar brand to do slash a form class equals form inline. Input class equals form control Mr. SM2 type equals search, placeholder equals search, area label equals search, slash button class equals btn outline info my SM0 type equals submit, search slash button slash form slash nav div % block. Content % in block content % slash div slash body HTML. The second template file is index HTML, which lists any existing to-do items and includes the form to create or delete a to-do item. a snippet of the index. HTML file is shown in the following code, the index. HTML file also extends the base HTML template, which allows the Bootstrap navigation bar implemented in base HTML to be inserted in this page and every page that extends it, %extends. Base HTML %, load static %, block content div Django app equals task manager, div class equals container mt5, div class equals content, h1 to do list /h1. P class equals tagline, Django to do app /pform action, method equals post, %CSRF token CSRF token for basic security, div class equals input container, input type equals text, ID equals description, class equals task name, placeholder equals, what do you need to do? Name equals description, required /label for equals description, description /label /div class equals input container half last, I class equals fa caret down select arrow /emphasis select ID equals category, class equals task category, name equals category select, option class equals disabled, value equals, choose a category /option % for category and categories %, option class equals, value equals, category. Names name equals, category, names of category. Name /option, % and 4%, /select label for equals category, category /label div class equals, input container half last right, input type equals date, ID equals due date, class equals task date, name equals date, /label for equals due date /label div class equals row, button class equals task add, name equals task add, type equals submit, I class equals fa plus icon /emphasis add task. /button class equals task delete, name equals task delete, form new validate equals, type equals submit, onclick equals $, input hash sublist. Click, I class equals fa trasho icon /emphasis delete tasks /button /div ol class equals task list, % for to do and to do's %. Django template lang for loop li class equals task item, input type equals checkbox, class equals task checkbox, name equals checkbox, ID equals, to do, id value equals, to do. Id /label for equals, to do. Id span class equals complete, to do. Title /span /label span class equals category, to do. Category, to do. Category /span, to do. Category /span strong class equals task date, I class equals fa calendar /emphasis created, to do, created, do, to do. Category /span, to do. Due date /strong, to do. Category /span /lie, % in 4%, /ol, task list /form /div, content /div, container /div, % in block %. The first step to access the to-do Django web application is to restart the Django server using the following command. Python manage, py-run-server next, launch a browser and navigate to http://localhost 8000. The page highlighted in figure 11/27 should appear. Screenshot of to-do list with description, category, and due date sections, as well as add task and delete tasks buttons. Figure 11/27. Once the Django server is restarted, this page should appear at http localhost 8000, rendered in Django, a registered trademark of the Django Software Foundation, attribution, copyright Rice University, OpenStax under CC by 4. 0 license to create a to-do list, fill out the form and click the Add Task button as shown in figure 11/28. Screenshot of to-do list with description, category, due date sections, add task, delete tasks buttons. And write an article on how to create a Django web application next to a work button. Figure 11/28. This figure shows how the to-do list should appear after using the Add Task button to create a to-do list. Rendered in Django, a registered trademark of the Django Software Foundation. Attribution, copyright Rice University, OpenStax, under CC by 40 license. In addition, the to-do item should also be viewable in the API that was created. This should appear as outlined in figure 11/29. Screenshot of to-do list viewable in API. Figure 11/29. Once the to-do item is created, it should be viewable in the API. Rendered in Django, a registered trademark of the Django Software Foundation. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Learning objectives. By the end of this section, you will be able to create a to-do web application with Bootstrap, React, and Node, create a Node backend, build the controller, set up the REST API, create the React frontend, connect the React frontend to the Node backend. In the previous section, you created a simple to-do application using Bootstrap and Django. In this section, you will continue to use Bootstrap to create another simple to-do application, but instead of working with Django, you will use React and Node, React or React. JS is a JavaScript library popular to build user interfaces. Node or Node. JS is a JavaScript runtime environment that provides users with the tools to develop web applications, as well as servers, scripts, and command line tools. Creating a to-do web application with Bootstrap and React and Node. When creating a to-do web application using React and Node, React serves as the front end, handling the user interface, as well as getting and setting data via HTTP requests using Axios. Node serves as the back end, using a REST API built with Express.js and the Mongoose.js Object Data Modeling, ODM, to interact with a MongoDB database. Prerequisites to build the to-do application using Bootstrap, React, and Node. You will need the following software components: React v17, 02 Bootstrap v4, 50 Node v14, 17. 5 Express.js v4, 17.2 Mongoose.js v6, 19 and Axios v0, 21, 0. To begin, download and install Node. Creating the Node backend. Several steps are needed to build the Node application backend required for the to-do application. This section will explain each of these steps. Link to Learning. Node is a JavaScript runtime environment that provides users with the tools to develop web applications, as well as servers, scripts, and command line tools. Node, which is free, is open source and cross-platform. It was designed to develop network applications that are scalable, managing many connections simultaneously. Unlike the typical inefficient concurrency model, with Node, a callback is fired with each connection, and Node sleeps unless work needs to be done. Creating the Node app. Before you can create the to-do application backend, you should create a Node app. To accomplish this, create the directory nodebekend/ and navigate into it. Next, run the following command to initialize the Node application. npm init. After running this command, follow the prompt, which is highlighted in Figure 11. 30. Screenshot of prompts for Node.js, Figure 11. 30. This prompt appears when the Node application is initialized. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. After the Node application initialization is completed, a package JSON file is generated as shown in the following code. Name, nodebekend, version, 100, description, to-do web application with Bootstrap, React.js, and Node.js, main, server. JS scripts, test, echo \error, no test specified \, and an exit 1, keywords, Bootstrap, React as Node.js, Express, MongoDB, REST, API, author, license. ISC dependencies, body parser, 1, 19.1, cores, 2.8.5, Express, 4, 17.2, Mongoose, 6, 1.9, setting up the Express web server. Once the Node application is initialized, the next step is to set up the Express web server. To do this, use the following command to install Express. Mongoose. Mongoose is a library for MongoDB that is used to interact with MongoDB by facilitating the modeling of data as objects and other dependent packages in the nodebekend/ directory. npm install Express Mongoose body parser cores. Save next. Create the Express web server by going to the nodebekend/ directory, create the server, JS file, and add the following code. Const express equals require, express. Const body parser equals require, body parser. Const cores require, cores. Const app equals express. Var cores options equals origin, HTTP. Localhost 8081, app, use cores options. Parse requests of content type application / JSON app, use body parser, JSON. Parse requests of content type application / XWWW form Erlang encoded app, use body parser. Erlang encoded, extended, true, roots app, get, /rec, raise equals raise. JSON message, welcome to the to-do web app. You require, route /to-do, roots, JS, app, set port, listen for requests, const port equals process, env, port 8080 app. Listen port equals console, log server is running on port. Once you use the code to import Express, you can build the REST APIs. The body parser package is used to create and parse the request object. The cores package is used to serve as middleware for Express that enables CORS. The Express web server will run on port 8080 as the default port. Use the following command to start the server, node server. JS in a browser, navigate to http://localhost 8080. The following page shown in Figure 11, 31 renders. Screenshot of start page of Express web server, Figure 11. 31 Once the Express web server is started, this page should appear at http://localhost 8080 rendered in Node. Attribution: Copyright Rice University, OpenStax under CC by 4. 0 License: Configuring the MongoDB database and Mongoose after the Express web server is created. The next step is to configure the MongoDB database and Mongoose. To do this, in the node-begin/directory, create the config/directory. Then, in the config/directory, create the file db config.js and add the following code. This specifies the database connection URL to the MongoDB database. Module exports equals URL MongoDB localhost 27017/to-do-db. Once the MongoDB connection URL is configured, the next step is to add code to connect to the database using Mongoose. To do this, in the node-begin/directory, create the models directory. In the models directory, create the index.js file and add the following: const db config equals require config/db config.js const mongoose equals require mongoose promise equals global promise const db equals db mongoose equals mongoose db url equals db config url db to-dos equals require /to-do model.js mongoose module exports equals db. Next, the node-begin/server JS file needs to be updated to enable the Express web server to establish a connection with the MongoDB. The code for this is shown in the following snippet. Const db equals require models db mongoose connect db url use new url parser true then equals console log connected to the database successfully. Catch error equals console log cannot connect to the database process exit. Once the database connection code is completed, the next step is to create the Mongoose model. To do this, in the node-begin/models/directory, create the file to-do model.js and add the following code. This code defines a Mongoose schema for the to-dos model, which results in the creation of a to-dos collection in the MongoDB database. Module exports equals mongoose equals var schema equals mongoose. Schema, title, type string required true, content, type string required false, created, type string default date, now, required. True due date, type string required true, category, type string required true, schema, method to JSON function, const v id, object equals this, to object, id equals id. Return object, const to-dos equals mongoose, model, to-dos, schema, return to-dos. Building the controller. The next step is to build the controller. The controller contains code that calls the Mongoose CRUD functions to interact with the MongoDB database. To build the controller, in the node-begin/directory, create the controller's directory. Then, in the controller's directory, create the file to-do controller.js and add the code as shown. The code implements the CRUD functions create, find all, find one, update, delete, and delete all. Const db equals require models const to-dos equals db to-dos. Create and save a new to-do item exports. Create equals rec raise equals validate record data if rec body title raise status 400 send message title cannot be empty. Return if rec body category raise status 400 send message category cannot be empty. Return if rec body due date raise status 400 send message due date cannot be empty. Return. Create a to-do item const to-do equals new to-dos title rec body title content rec body content category rec body category due date rec body due date. Save the to-do item in the database to-do. Save to-do, then data equals raise send data. Catch error equals raise status 500 send message message an error occurred while creating the to-do item. Retrieve all to-do items exports. Find all equals rec raise equals const title equals rec query title var condition equals title regex new reg exp title options. To-dos find condition, then data equals raise send data. Catch error equals raise status 500 send message message an error occurred while retrieving to-do items. Retrieve a to-do item by id exports. Find one equals rec raise equals const id equals rec params id to-dos find by did, then data equals if data raise status 404. Send message error finding to-do item with id plus id else raise send data. Catch error equals raise status 500 send message error retrieving to-do item with id equals plus id. Update a to-do item by id exports. update equals rec raise equals if rec body return raise status 400 send message specify a to-do item to update to-do item cannot be empty. Const id equals rec params id to-dos find by id and update id rec body use find and modify false then data equals if data raise status 404 send message cannot update to-do item with id equals $id to-do item was not found else raise send message the to-do item was updated successfully catch error equals raise status 500 send message error updating to-do item with id equals plus id delete a to-do item by id exports delete equals rec raise equals const id equals rec params id to-dos find by id and remove id use find and modify false then data equals if data raise status 404 send message cannot delete to-do item with id equals $id to-do item was not found else raise send message the to-do item was deleted successfully catch error equals raise status 500 send message error deleting to-do item with id equals plus id delete all to-do items from the database exports delete all equals rec raise equals to-dos delete many then data equals raise send message data deleted count all to-do items were deleted successfully catch error equals raise status 500 send message message an error occurred while deleting all to-do items. Set up the REST API once the controller is built. The next step is to set up the REST API. A client will send HTTP requests, e.g. get, post, put, and delete, to the REST API endpoints that determine how the server will manage these requests and provide a response. To do this, routes for the REST API are first defined. In the node_begin/ directory, create the routes directory. In the routes directory, create the file to do, routes.js, and add the following code. In this code, the routes require access to the CRUD functions declared in the controller. Module, exports equals app equals, const to-dos equals require, controllers/to-do, controller.js. var router equals require, express, router, create a new to-do item router, post/to-dos, create, retrieve all to-do items router, get/to-dos, find all. Retrieve a to-do item by id router, get/id to-dos, find one, update a to-do item by id router, put/id to-dos, update, delete a to-do item by id router. Delete/id to-dos, delete all to-do items router, delete/to-dos, delete all, app, use/API/to-dos router. The next step is to update node_begin/server. JS to import the routes shown in the following code. Routes app, get/rec raise equals raise JSON message, welcome to the to-do web app. You require routes/to-do, routes.js app. Set port, listen for requests, const port equals process. Env, port 8080, app, listen port equals console, log server is running on port. The next step is to run the Express web server to test the CRUD functions and interact with the MongoDB database. To do this, run the following command, node server. JS linked to learning as an API platform, Postman can be a useful programming interface to build and use APIs. Postman is simplified, making it easier to build APIs quickly. With Postman, developers can also test and modify APIs to ensure they meet specifications. To test the REST API, use Postman, which is an API platform testing tool that can be used as a client. To accomplish this, follow these steps. Install and launch Postman. Select Post as the request method. Enter the URL http localhost 8080/API/to-dos to test creating a to-do item. In the data input frame, select body. Select raw and JSON for the data format. Enter a JSON object representing a to-do item to be created as shown. Click Send. After you follow these steps, the bottom frame should receive a response with status 200 OK, indicating the request was handled successfully. The body of the created to-do item will also display along with a generated id field. You can use this method to test all the CRUD functions, creating the React front end. Once you complete these steps and have the back end of the to-do web application up and running, the next step is to implement the front end using React. This section will outline the steps to accomplish this. Linked to Learning React is a JavaScript library popular to build user interfaces. It relies on individual pieces known as components, which are JavaScript functions. React components are created using code and markup, and once created, React components can be combined to develop applications, screens, and web pages. React also has the capability to be added to HTML pages, rather than building an entire page using React. Creating the React app. To create the React app, the first step is to run the following command. This should be done in a directory that is outside and separate from the node backend/directory. npx create React app React frontend. Once you run the command, it will generate the React application files in the React frontend/directory, which is shown in Figure 11. 32. List of React.js application files in React frontend. Figure 11. 32. This shows the React application files in the React frontend/directory, rendered in React by Meta Open Source Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. The next step is to navigate into the React frontend/directory and launch the React application to confirm the React frontend application was created successfully. At this point, this application is not connecting to the node backend, so it launches a default React page. Run the command, which will automatically launch a browser page to http://localhost 3000. npm start. You will see the following, as illustrated in Figure 11. 33. Screenshot of start page of React.js frontend application. Figure 11. 33. When the React frontend application is created successfully, this page launches at http localhost 3000. Credit React by Meta Open Source. Installing Bootstrap and other dependencies. The next step is to install the packages for Bootstrap and Reactstrap, which are necessary to use Bootstrap in a React app. To do this in the React frontend/directory, run the following commands. npm install Bootstrap at 4.60 Reactstrap at 8.90 legacy peerdeps. npm install React Bootstrap. Next, import the Bootstrap 4 CSS file into the React application. To do this, open React frontend/src/index.js and add the following Bootstrap import. Import React from React. Import React DOM from React DOM. Import bootstrap/dist/css/bootstrap. CSS, import index, CSS, import app from app, import report web vitals from report web vitals, React DOM, render React. Strict mode app//react, strict mode document, get element by ID root. If you want to start measuring performance in your app, pass a function to log results, for example. Report web vitals console, log, or send to an analytics endpoint. Learn more, https://bit.ly/CRA vitals report web vitals. Create the React components. The next step is to create the React components. The React user interface is rendered from the React frontend/src/app, JS component, the React frontend/src/app. JS file is generated when the React application is created. This is the main component of the React application, and all other components are added to the React frontend/src/app, JS component. A few imports are added to the React frontend/src/app, JS file, as shown in the following code. This includes an import for app, CSS. Customized CSS rules are added to React frontend/src/app. CSS, import logo from logo. SVG, import app, CSS, import React, component from React, import modal from components modal, import nav from components nav component, import Axios from Axios, import button form group label input from Reactstrap to compare with the Django web application in 11. 2 sample responsive WAD with Bootstrap and Django customized CSS rules were added to the style CSS file in the static directory, as described in creating the templates. Next, look at the following code, which shows app is a class component that extends React's component class. All state data is added to this state variable in the constructor. Class app extends component constructor props, super props. This state equals to-do checked, false to-do list, categories, description, modal false active item, title, description, completed false. The next code snippet shows that every class component must include a render function. This function returns the components that construct the user interface for the to-do web application. Render return main nav/div class name equals container mt5pl3 h1 to-do list /h1 form div class name equals input container form group label html for equals description /label input type equals text id equals description name equals description placeholder equals description value equals this. State description /form group /div class name equals input container half last form group label html for equals category /label input id equals category class name equals task category, type equals select, name equals category select, value equals this. State. Contact type option class name equals disabled, value equals. Choose a category / option work / option personal / option / input / form group / div class name equals. Input container last right form group label HTML for equals description due date / label input type equals text. ID equals description name equals description placeholder equals due date /dd/ei value equals this. State description / form group / div class name equals row button class name equals task add name equals task add type equals submit edit / button class name equals task delete ml name equals task delete type equals submit onclick equals dollar input #sublist. Click delete / button / div / form all class name equals task list this. Render items /ul /div /main, connecting the React front end to the Node back end. The final step to create the to-do web application is to configure the React application so it can make requests to the API endpoints of the Node application. The React application uses Axios to fetch data by making requests to a given endpoint. To install Axios, run the following command in the React frontend / directory, npm install Axios at 0.21. Next, add a proxy to the Node application. The proxy will help tunnel API requests from the React application to HTTP, localhost 8080 where the Node application will receive and handle the requests. To do this, open the React frontend / package, JSON file and add the following proxy. Name, React frontend, version, 010, private. True proxy, HTTP, localhost, 8080, dependencies. The next step is to create a service on the front end to send HTTP requests to the back end. This process uses Axios and is similar to how routes were created on the back-end side. The service will export CRUD functions and a finder method to interact with the MongoDB database. To do this, in the React frontend / directory, create the services directory. Then, in the services directory, create the tile to do service, JS, and add the following code. Import Axios from Axios. Const getall equals return Axios. Get /API /to do / const get equals id equals return Axios. Get /API /to do $.id. Const create equals data equals return Axios. Post /API /to do's data. Const update equals id data equals return Axios. Put /API /to do's $.id data. Const remove equals id equals return Axios. Delete /API /to do's $.id. Const remove all equals return Axios. Delete /API /to do's. Export default getall get create update remove all. Finally, to complete this step, update React frontend /app JS to the following to call the services. Handle submit equals item equals var data equals id title content due date category to do service, create data. Then raise equals this, refresh list, catch error equals console, log error, handle update equals item equals var data equals id title content due date category to do service, update id data, then raise equals this, refresh list, catch error equals console, log error, handle delete equals item equals to do service, remove id then raise equals this, refresh list, catch error equals console, log error, refresh list equals to do service, getall, then raise equals this, set state, to do list, raise data. Catch error equals console, log error. Once this is completed, run both the Express web server and the React app using the following commands. Node server, JS npm start. When this is done, use the form shown in figure 11. 34 to create a new to-do item. Screenshot of to-do list form to create items. Figure 11. 34 Once the to-do web application is created using Bootstrap with React and Node, this form can be used to create to-do items. Rendered using Bootstrap, under MIT license copyrighted 2018 Twitter, with React by Meta open source and Node. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Learning objectives. By the end of this section, you will be able to update the to-do web application with Bootstrap, React, and Django, extend the Django backend to support the React frontend, connect the React frontend to the Django backend. Previously, you learned how to build a to-do web application using Bootstrap and Django, and then using Bootstrap with React and Node. This section will review the steps required to update the To-Do web application using Bootstrap with React and Django. Updating the To-Do web application with Bootstrap, React, and Django. In this section, the To-Do web application implemented will build on the Django application covered in 11. 2 sample responsive WAD with Bootstrap and Django, as well as the React application explored in 11. 3 sample responsive WAD with Bootstrap, React, and Node. For this version of the To-Do web application, React serves as the front end, handling the user interface to get and set data via HTTP requests. Django serves as the back end. Prerequisites to build this version of the To-Do application: you need Python v3, 9.4 pip v21, 3.1 Django v4, 0.1 Django REST Framework v3, 13.1 Bootstrap v4, 5.0 Django Cores Headers v3, 11.0 React v17, 0.2 and Axios v0, 21.0. To begin, complete the following steps. Activate the venv used in section 11a2. cd pi 394 venv Windows, source, scripts activate macOS, source, /bin activate install in the local programming environment Django Cores Headers pip install Django Cores Headers = 3. 11. Link to learning when using Django Cross-Origin Resource Sharing, CORS. Headers can be a valuable tool to allow a Django application to accept in-browser requests that come from other origins. With Cores Headers, other domains can access your resources, but only if permitted. When used appropriately, this makes CORS an important tool to boost a website's security. Extending the Django backend to support the React front end to create a To-Do web application using React as a front end to the Django backend. The Django project requires a couple of configurations. Open To-Do app/settings, pi and add coresheaders to installed apps as in the following code. Installed apps equals Django, contrib, admin, Django, contrib auth, Django, contrib content types, Django, contrib sessions, Django. Contrib messages, Django, contrib, static files, coresheaders, REST framework, to-do. By configuring the Django project with CORS, the Django application will be allowed to accept in-browser requests that come from other origins. To add CORS, add the Cores middleware to middleware, as shown in the following code. Middleware equals Django, middleware security, security middleware, Django, contrib sessions, middleware, session middleware, Django, middleware, common. Common middleware, Django middleware, CSRF, CSRF view middleware, Django, contrib auth middleware, authentication middleware, Django, contrib messages, middleware, message middleware, Django middleware, clickjacking. Xframe options middleware, coresheaders, middleware, Cores middleware. After completing this step, scroll to the bottom of the settings, pi file and add the following variable, #add CORS whitelist for localhost 3000 since the React frontend will be served on port 3000 Cores origin whitelist equals HTTP, localhost 3000. Link to learning Axios is an HTTP client for Node that manages asynchronous HTTP requests. Axios is free and open source with built-in security measures. Axios uses clean, efficient syntax to manage promises and works well with Node, as well as browser environments. Visit this page on Axios to learn more. Connecting the React front-end to the Django back-end next, the React application must be configured so it can make requests to the API endpoints of the Django application. The React application uses Axios to fetch data by making requests to a given endpoint. To install Axios, run the following command in the React frontend /directory, npm install Axios at 0.21. 1. Next, add a proxy to the Django application. The proxy will help tunnel API requests from the React application to HTTP, localhost 8000, where the Django application will receive and handle the requests. To add the proxy, open the React frontend /package, JSON file and add the following code. Name, React frontend, version, 0.1. 0. Private, true proxy, HTTP, localhost, 8080, dependencies. After completing this step, open the React frontend /src/app. JS file and import Axios as shown in the following code. Import app CSS, import React, component from React, import modal from components modal, import nav from components nav component, import Axios from Axios, import button form group label input from React-Strap. To update the React frontend /src/app. JS file, add the following code. The handle submit function will use Axios to make requests to the Django API endpoints to create and delete to-do items. handle submit equals item equals this, toggle. If item id axios, put /API /to-do $item, ID /item, then raise equals this, refresh list, return, axios, post /API /to-do /item, then raise equals this. Refresh list, handle delete equals item equals axios, delete /API /to-do $item, ID then raise equals this, refresh list. When these steps are complete, start up the Django server and then start up the React application using the following commands respectively. Python manage. py-run-server npm start to access the Django REST API, navigate to http://localhost 8000/API/. This is similar to the steps completed in 11. 2. Sample responsive WAD with Bootstrap and Django. Click on the categories API path to enter 2 categories, as seen in Figure 11. 35. Screenshot of entry page to Django REST API, Figure 11. 35. After navigating to http://localhost 8000/API/ and following the instructions provided, this page will appear to allow access to the Django REST API. Rendered in React by Meta Open Source. Attribution. Copyright Rice University, OpenStax, under CC BY 4.0 license. When the React application starts up, a browser page will automatically launch for navigating to HTTP. Localhost 3000 and the user interface should render. Figure 11. 36 shows the page on which to create a to-do item. Screenshot of user interface page for React.js. Figure 11. 36. After the React application starts up, this user interface will appear. Rendered in React by Meta Open Source. Attribution. Copyright Rice University, OpenStax, under CC BY 4.0 license. At this point, revisit the Django REST API. Figure 11. 37 shows that the to-do item should be accessible via the to-do's API path. Screenshot of page for creating a to-do list. Figure 11. 37. Once the to-do web application is updated using Bootstrap with Django and React, this page should appear to allow users to create a to-do list. Rendered using Bootstrap under MIT license, copyrighted 2018 Twitter. With Django a registered trademark of the Django Software Foundation, and React by Meta Open Source. Attribution. Copyright Rice University, OpenStax, under CC BY 4.0 license. Learning objectives. By the end of this section, you will be able to create a to-do native mobile application with React Native or Node. Create a React Native app and its components. Connect the front-end native app with the back-end Node app. In the previous sections, you worked with Bootstrap, Django, React, and Node to build versions of a to-do web application. In this section, you will learn how to use React Native and Node to develop a to-do application for mobile devices. You are already familiar with Node. Like React, React Native is an open-source JavaScript framework used to build native applications for mobile devices. Link to learning. React Native uses the React JavaScript library to enable native development and build user interfaces for mobile devices. React Native has the flexibility to work with Xcode, which is the IDE for various platforms. Released by Facebook, now Meta, in 2015, React Native has become increasingly popular among developers, creating a to-do web application with React Native and Node. This application uses React Native and Node to implement a simple to-do mobile application. This application builds on top of the React and Node application discussed in 11. 3. Sample responsive WAD with Bootstrap, React, and Node. For this version of the application, React Native serves as the front end, handling the user interface and getting and setting data via HTTP requests. Node serves as the back end that makes use of the API built using the Django REST framework in 11. 2. Sample responsive WAD with Bootstrap and Django. Prerequisite. To build the to-do mobile application using React Native and Node, you need React Native v0, 67 Node v14, 17.5 ExpressJS v4, 17. 2. Mongoose.js v6, 19 and Axios v0, 21, 0. This to-do application will run using the Android emulator and will use Android Studio v202111. Link to learning. Xcode is the IDE for the Apple platform. For Apple, React Native provides developers with the tools needed for cross-platform development that creates user-friendly apps on mobile devices. To begin, download and install an emulator for your intended platform, iOS or Android. If you plan to run the native app on an iOS device or emulator, download and install Xcode, which is Apple's IDE that enables application development for Apple's platforms. If you plan to run the native app on an Android device or emulator, download and install Android Studio, which enables application development for Android mobile operating systems. Figure 11. 38 shows how to set up the Android emulator. Launch Android Studio. From the top navigation, select Tools Device Manager. Click on Create Device. In the Select Hardware pop-up, select Pixel 5 and click Next. On the next page, select Pi Download. Click on the download link to obtain an image as shown. Click Next followed by Finish. Screenshot of page to set up Android emulator. Figure 11. 38. This shows how to set up the Android emulator. Android Studio is a trademark of Google LLC. Once the image has been created, it will appear in the device manager. Next, click on the Start button to launch the emulator. When the emulator is launched, it will turn on, as shown in Figure 11. 39. Screenshot of emulator showing a cell phone screen. Figure 11. 39. This is how the emulator will appear after it is launched. Android Studio is a trademark of Google LLC. Link to learning. Xcode also integrates well with Android Studio for developing Android apps. Android Studio is the IDE for Android devices, creating the React Native app. After launching the emulator, create the React Native app by running the following command in a directory outside and separate from the node_backend/ directory. Figure 11. 40 shows the React Native application files in the React Native frontend/ directory. npx React Native, init React Native frontend. Screenshot of React Native application files in the React Native frontend/ directory. Figure 11. 40 When the React Native app is created, it will generate the React Native application files in the React Native frontend/ directory, rendered in React Native under MIT license, attribution. Copyright Rice University, OpenStax, under CC by 40 license. Next, navigate into the React Native frontend/ directory and launch the React Native application to confirm that the React Native frontend application has been created successfully. At this point, the application is not connected to the node backend and will launch the Metro bundler, which bundles the JavaScript code that is deployed on the mobile device or emulator when the React Native frontend application is successfully completed. When this is done, run the command. Figure 11. 41 shows the page in the terminal. npx React Native Start. Screenshot of React Native Start command. Figure 11. 41 This page will appear when the React Native Start command is run. Credit React Native under MIT license. The next step is to open another terminal, navigate to the React Native frontend/ directory, and run the following command. This will build the frontend code and deploy it on the emulator, which may take a few minutes. npx React Native Run Android. When the application is successfully built, Figure 11. 42 shows what should appear in the second terminal. Screenshot of code. Figure 11. 42 This code should appear in the second terminal when the React Native application is successfully built. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Figure 11. 43 shows how the native application should appear in the emulator. Welcome page for React Native in emulator. Figure 11. 43 Once the React Native application is successfully built, this is how the native application should appear in the emulator. Android Studio is a trademark of Google LLC. Creating the React Native app components. The packages used by the React Native app for navigation and other features are different from the packages used by React. To install the required packages in the React Native frontend/ directory, run the following list of commands. npm install at React Navigation Native at 6.0. 7. npm install at React Navigation Native Stack at 6.3.0. npm install Axios at 0.25.0. npm install Moment at 2.29. 1. npm install React Native Modal at 13.0.0. npm install React Native Safe Area Context at 3.3.2. npm install React Native Screens at 3.10. 2. npm install React Native Snackbar at 2.4.0. npm install React Native Vector Icons at 9.0.0. The first step is to create the to-do component. In the React Native frontend/ directory, create the directory src/screens/. In the src/screens/ directory, create the file to-do list, JS. The following code shows the imports required to create the screen components. Import React, use state, use effect from React, import. View, text, style sheet, text input, flat list, touchable opacity, dimensions, status bar, alert from React Native. Import Axios from Axios, import colors from utils/colors, import material icon from React Native Vector Icons material icons, import material community icon from React Native Vector Icons material community icons. Import modal from React Native modal, import snackbar from React Native snackbar, import duration from moment. Once this is done, the following code includes the return function that renders the screen components. Return, view style equals styles, container, status bar background color equals colors, DARKLT, text style equals styles, heading welcome to-do list app/text, text style equals styles, heading your tasks/text, to-dos length equals 0, view style equals styles, center, material community icon, name equals note multiple, size equals 90, color equals colors, LIGHTALT, text style equals styles, no tasks text no tasks added /text, /view, view style equals styles, to-dos container, flat list, data equals to-dos, render item equals view style equals styles, to-do, text, style equals item, complete, styles, completed style, styles, text, item title, /text, touchable opacity, style equals styles, delete to-do, on press equals delete to-do item, text style equals color, colors, white text/text, /touchable opacity, /view, /view, touchable opacity, style equals styles, add button, on press equals, set modal active, true, material icon name equals add, size equals 32, color equals colors, light, /touchable opacity, modal is visible equals modal active, animation in equals slide in up, animation out equals slide in down, view style equals styles, modal view, touchable opacity, style equals styles, modal close btn, on press equals set modal active false, text style equals styles, modal close btn text/text, /touchable opacity, text style equals styles, add task heading add task/text, text input, style equals styles, task input, placeholder equals enter task here, on change text equals set new to do, text, value equals new to do, touchable opacity style equals styles, create btn on press equals add to do, text style equals styles, create btn text create task/text, /touchable opacity, /view, /modal, /view. The following code creates the modal pop-up screen that is used to create a to-do list. Modal is visible equals modal active, animation in equals slide in up, animation out equals slide in down, view style equals styles, modal view, touchable opacity, style equals styles, modal close btn, on press equals set modal active false, text style equals styles, modal close btn text/text, /touchable opacity, text style equals styles, add task heading add task/text, text input, style equals styles, task input, placeholder equals enter task here, on change text equals set new to do, text, value equals new to do, touchable opacity style equals styles, create btn on press equals add to do, text style equals styles, create btn text create task/text, /touchable opacity, /view, /modal. Next, update the React Native frontend /app JS file as shown in the following code to render the screen components declared in the to-do list. JS file, import React from React, import navigation container from @React Navigation Native, import create native stack navigator from @React Navigation Native Stack, import to-do list from src/screen/to-do list. Const stack equals create native stack navigator. Const app equals return navigation container. Stack navigator. Stack screen. Name equals to-do list. Component equals to-do list. Options equals header shown, false. Slash stack navigator slash navigation container. Export default app. When this is done, relaunch the Metro bundler and deploy the native application by running the following commands. npx react native start. npx react native run Android. Next, create a to-do item, figure 1144. Screenshot of page to create to-do items, figure 1144. After relaunching the Metro bundler and deploying the native application, this screen allows users to create a to-do item. Android Studio is a trademark of Google LLC. After the to-do item is created, it should appear on the main screen as seen in figure 1145. Screenshot of welcome page for creating your to-do list app, figure 1145. Here is how the to-do item should appear on the main screen. Android Studio is a trademark of Google LLC. Connecting the front-end native app with the back-end Node app. The next step is to connect the front-end React Native app with the back-end Node app. To do this, open React Native frontend /src/screen/totalist.js. Add the API base variable and configure the IP address to the local computer, running the Express web server, as shown in the following code. Import Axios from Axios. Import COLORS from utils/colors. Import material icon from React Native Vector Icons Material Icons. Import material community icon from React Native Vector Icons Material Community Icons. Import modal from React Native modal. Import snackbar from React Native snackbar. Import duration from moment. Const width equals dimensions. Get window width. Const API base equals HTTP 192.168.183.8080. Next, add the Axios calls to interact with the REST API provided via the Express web server to interact with the MongoDB database. Const todos set todos equals use state. Const modal active set modal active equals use state false. Const new to do set new to do equals use state. Use effect equals get todos. Const get todos equals Axios get $API base /API /todos. Then response equals set todos response data catch error equals console error snackbar show text plus duration snackbar length long background color reds text color colors white const complete to do equals async id equals const data equals await Axios put $API base /API /todos $ID set todos equals todos map to do equals if to do id equals data id to do complete equals data complete return to do const delete to do equals async id equals const data equals await Axios delete $API base /API /todos $ID set todos equals todos filter to do equals to do id equals data id const add to do equals async equals if new to do equals alert error please enter a task first return else await Axios post $API base /to do /new text new to do then function response const data equals response data set todos data set modal active false set new to do catch function error console log errors. Learning objectives. By the end of this section, you will be able to build a hybrid Ethereum blockchain Web3. Zero application, create the React app and install dependencies, create the smart contract, create the front-end React components, add Web3 to the React app, configure the React app to communicate with the smart contract. So far, this chapter has explored how to develop a to-do web application, as well as a to-do mobile application, using Bootstrap, Django, React Native, and Node. In this final section, you will learn how to create a simple to-do application using React with Web 3.0 powered by Ethereum smart contracts on the blockchain, creating a to-do Ethereum blockchain Web 3.0 application. As you have learned, to-do applications can be created using different tools. In this section, you will explore the Ethereum blockchain, which creates a secure peer-to-peer network through the use of a smart contract, which is a secure digital agreement that enables users to transact directly with each other via the blockchain. You will use React to create a to-do Ethereum blockchain Web 3.0 application. Linked to Learning Ganache is a personal Ethereum blockchain environment that provides developers with the means to use a private blockchain for development and testing. Ganache can emulate the Ethereum blockchain, and because it is a private blockchain, it allows developers control over development and testing processes. Prerequisites to build the to-do Ethereum blockchain Web 3.0 application: you should use React v17, 02 Bootstrap v4, 50 Node v14, 17.5 Web3.js v1, 22 Truffle v5, 2 and Solidity v0, 8.11. In addition, Ganache is used as the personal blockchain for development. To begin, do the following: download and install Ganache. Launch Ganache and choose the Quick Start Ethereum option as seen in Figure 11.46. Screenshot of Ethereum option. Figure 11.46. This is the Quick Start Ethereum option that is available after installing Ganache. Credit Ganache under MIT license. The next step is to install the MetaMask Chrome plugin. Configure the MetaMask account and log in. Creating the React app. Previously in this chapter, you created React apps. For this application, you need to create a new React app. To create the new React app, run the following command: npx create React app ethreact install Bootstrap, Web3, and other dependencies. To use Bootstrap and Web3 in a React app, corresponding packages must be installed. To do this in the ethreact/directory, run the following commands: npm install Bootstrap at 4.60 Reactstrap at 8.90 Legacy PeerDeps, npm install React Bootstrap, npm install Web3 at 1.22. Next, import the Bootstrap CSS file into the React application. Open ethreact/src/index.js and add the following Bootstrap import. Import React from React. Import React DOM from React DOM. Import Bootstrap/dist/css/bootstrap. CSS. Import index. CSS. Import app from app. Import Report Web Vitals from Report Web Vitals. React DOM render React. Strict mode app//React. Strict mode document. Get element by ID root. If you want to start measuring performance in your app, pass a function to log results, for example. Report Web Vitals console. Log or send to an analytics endpoint. Learn more: https://bit.ly/CRA Vitals Report Web Vitals. Link to Learning. Truffle provides a suite of tools that can be used to develop smart contracts. Truffle offers end-to-end development that includes the ability to develop, test, and implement smart contracts, while using Truffle to manage the workflow. Creating the smart contract. To develop the Ethereum smart contract, you will use the Truffle framework, which is a popular suite of tools used to develop smart contracts. Implement the Truffle framework using Solidity, which is a high-level, object-oriented language that is focused on the implementation of smart contracts. To use the Truffle framework, in the ethreact/directory, run the installation following command: npm install gtruffle at 5.02. To set up the React app. To use Truffle, in the ethreact/directory, run the following command, which may take several minutes. Truffle init. When the initialization is completed, the contracts, directory, and migrations Sol file will be generated. In addition, the Truffle config.js file will be generated, as highlighted in Figure 11.47. Screenshot of Truffle config.js file. Figure 11.47. Here is the Truffle config.js file, rendered with Truffle by Truffle Security Co. under MIT license, attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. To create the smart contract, in the ethreact/contracts/directory, create the file to-do list, Sol, and add the following code. Pragma Solidity 0.50, contract to-do list, uint public task count equals 0, struct task uint id, string content, bool completed, mapping uint equals task public tasks. Event task created, uint id, string content, bool completed, event task completed, uint id, bool completed, constructor, public, create task, check out DAP University. Function create task, string memory content, public, task count ++, task count equals task count content false, emit task created, task count content false. Function toggle completed, uint id, public, task memory task equals tasks ID, task completed equals task completed, tasks ID equals task, emit task completed ID, task completed. Next, compile the smart contract. In the ethreact/directory, run the following command. Truffle compile. This command should provide a status confirming that the smart contract has been successfully compiled as seen in the following code. Compiled successfully using SALK 05, 16 plus commit, 9C3226C, Emscription, Clang figure 11, 48 shows how this process will generate a few files, including two JSON files in the build contracts directory and a migration file in the migrations directory. Screenshot of JSON and migration files. Figure 11, 48. These are the JSON and migration files generated when the smart contract is compiled, rendered using JSON attribution. Copyright Rice University, OpenStax, under CC by 40 license, the to-do list. JSON file in the build contracts directory is the Smart Contract Abstract Binary Interface, ABI file. This file contains the following: compiled bytecode from the Solidity Smart Contract code that can run on the Ethereum Virtual Machine, EVM, a JSON representation of the smart contract. Next, configure the React app to connect to the Ganache blockchain network. To do this, open the ethreact/truffleconfig JS file and uncomment the two sections shown. Under Networks, enable the connection host and port to the Ganache blockchain network. Ensure that the host and port are in sync with the following settings in Ganache development. Host 127.0.0. 1's localhost default, none port 7545, standard Ethereum port default, none networked, any network default. None. Next, under compilers, enable the SALK optimizer. Configure your compilers. SALK version 051, fetch exact version from SALK bin default. Truffle's version Docker true, use 051. You've installed locally with Docker default, false settings. See the Solidity docs for advice about optimization and EVM version optimizer. Enabled true runs 200, EVM version, Byzantium. Next, create a migration script to deploy the smart contract to the Ganache blockchain network. In the ethreact/migrations/directory, create the file to deploy contracts, JS, and add the following code. var to-do list equals artifacts, require /to-do list, sol, module. Exports equals function, deploy to-do list. The next step is to migrate the contract. In the ethreact/directory, run this command, truffle migrate figure 11. 49 displays how the contract will be migrated and provides the transaction details. You should make a note of the contract address in the output because it will be added to the config.js file later. Screenshot of transaction details for migrating contract. Figure 11, 49. Here are the transaction details for migrating the contract. Attribution, Copyright Rice University, OpenStax, under CC by 40 license. Linked to learning. Solidity is a high-level, object-oriented language used to implement smart contracts. Influenced by JavaScript, C++, and Python, Solidity is focused on the Ethereum virtual machine. Smart contracts implemented by Solidity are used for purposes like blind auctions, voting, and crowdfunding. Visit this page on Solidity to learn more. Creating the front-end React components. The to-do list component renders the user interface for the to-do app. In the ethreact/src/directory, create the components directory. In the components directory, create the file to-do list, JS, and then create the to-do list component. Import React component from React class to-do list extends component render, return div id equals content, form on submit equals event, prevent default, this, props, create task, this, task. Value input id equals new task, ref equals input equals this, task equals input, type equals text, class name equals form control, placeholder equals add task. Required input type equals submit, hidden equals true, /form ol id equals task list, class name equals list unstyled, this, props, tasks. Map task key equals return, div class name equals task template, class name equals checkbox, key equals key, label input type equals checkbox, name equals task, id default checked equals task. Completed ref equals input equals this, checkbox equals input, on click equals event equals this, props, toggle completed this, checkbox, name, /span class name equals content task, content /span /label /div, /ol id equals, completed task list, class name equals, list unstyled, /ol /div, export default to-do list, update the ethreact/src/app. JS to import and render the to-do list component. Render, return div nav class name equals navbar dark fixed top bg dark flexmd norep p0 shadow a class name equals navbar brand column3 column d2 mr 0 href equals hash to do slash ol class name equals navbar nav px3 lie class name equals nav item text norep d none d sm none d sm block small a class name equals nav link href equals hash span id equals account slash span slash a slash small slash lie slash ol slash nav div class name equals container fluid div class name equals row main role equals main class name equals call lg12 deflex justify content center this state loading div id equals loader class name equals text center p class name equals text center loading slash p slash div to do list tasks equals this state tasks create task equals this create task toggle completed equals this toggle completed slash main slash div slash div slash div. Adding Web3 to the React app. The next step is to add Web3 and configure it to connect to Ganache. To do this, open ethreact/src/app. JS, import the Web3 package, and add the code shown here. In this code, a Web3 connection is instantiated, providing the Ganache URL, HTTP. Localhost 8545. This enables the React app to connect to the blockchain. The blockchain account information is then accessed and added to the React app state object. In the ethreact/src/directory, create the file getweb3.js and add the code shown. This code creates a Web3 object via different connection approaches depending on the approach used, e.g. type of DApp browser using localhost. Import Web3 from Web3. Const get Web3 equals new promise. Resolve, reject equals wait for loading completion to avoid race conditions with Web3 injection timing. Window add event listener. Load async equals modern DApp browsers. If window Ethereum const Web3 equals new Web3 window. Ethereum try request account access if needed await window. Ethereum enable accounts now exposed resolve Web3 catch error reject error. Legacy DApp browsers, else if window, Web3, use missed meta masks provider. Const Web3 equals window, Web3, ORIG const Web3 equals window, Web3, current provider, enable, console, log, injected Web3 detected, resolve Web3. Fallback to localhost, use dev console port by default, else const provider equals new Web3, providers, HTTP provider, HTTP 127.0.0.1. 8545, const Web3 equals new Web3 provider, console, log, no Web3 instance injected using local Web3, resolve Web3, export default get Web3. Configuring the React app to communicate with the smart contract. To make the tasks from the smart contract available to the React app, create a config file, along with the contract address and ABI. To do this in the ethreact/src/directory, create the file config.js. Then, create two variables, TODOList address and TODOList ABI. Grab the contract address that was provided when the smart contract was deployed to the blockchain and assign it to TODOList address. Open the ethreact/build/contracts/to-do list JSON file and copy the ABI portion only and assign it to TODOList ABI. Export const TODOList address equals 0x9A93A9951 C1CACF0 sec 325 AD4E0 5D55 AD02. Export const TODOList ABI equals inputs. Payable false state mutability, non-payable type constructor anonymous false inputs, indexed false internal type, uint256 name id type. uint256, indexed false internal type, bool name, completed type bool name, task completed type event, anonymous false inputs, indexed false internal type. uint256, name, id type, uint256, indexed false internal type, string, name, content, type, string, indexed false internal type, bool name. Completed type bool name, task created type event, constant true inputs, name, task count, outputs, internal type, uint256, name, type. uint256, payable, false state mutability, view, type, function, constant, true inputs, internal type, uint256, name, type. uint256, name, tasks, outputs, internal type, uint256, name, id type, uint256, internal type, string, name. Content type string, internal type, bool name, completed type bool, payable, false, state mutability, view type, function, constant, false, inputs, internal type, string, name. Content type string, name, create task, outputs, payable, false, state mutability, non-payable type, function, constant, false, inputs, internal type, uint256, name. Id type uint256, name, toggle completed, outputs, payable, false, state mutability, non-payable, type, function, next, update ethreact/src/app, JS. Import get web3, JS and add the following code to the component did mount, lifecycle method. This will connect to the blockchain network and load the contract before the React components renders in the browser. Component did mount equals async equals try, get network provider and web3 instance. Const web3 equals await get web3, use web3 to get the user's accounts. Const accounts equals await web3, eth get accounts, get the contract instance. Const networkid equals await web3, ethnet, getid, let deployed network equals to-do list ABI. Network's network ID, const to-do list instance equals new web3, eth, contract, todolist ABI, deployed network and undeployed network. Address, set web3, accounts, and contract to the state, and then proceed with an example of interacting with the contract's methods. This set state web3 accounts to-do list contract, to-do list instance this. Run example, catch error, catch any errors for any of the above operations. Alert, failed to load web3 accounts or contract. Check console for details. Console, error. Launch the React app by running the following command. npm start launch a browser with the MetaMask plugin installed and navigate to HTTP. Localhost 3000, create a task.